Now, next session, we move to there's a resource people joined in this program. Mr. Nana Prakash, yes, okay, he is going to address the first session on Industry 4.0 and Smart Machines Architecture. So he is going to talk on this topic, to all of us on this first session. So on behalf of Department of Mechanical Engineering, Knowledge Institute of Technology, I do welcome Mr. Nana Prakash, yes, who is Executive Director of BGR Neo Limited. So welcome you, sir.
Good morning. Hi, everyone.
Yes, sir. Good morning, sir. Good morning, sir.
You're audible. You're audible, sir. Good morning and welcome, please.
Thank you, sir. Thank you for joining us. Ladies and gentlemen, I take this opportunity before we go into the formal session. Let me have the pleasure of introducing a resource person of this first session, Mr. Nana Prakash, who is the Executive Director at BGR Neo Limited. He is a seasoned technology and operations leader with over 30 years of experience in industrial automation, digital manufacturing, Industry 4.0, and in enterprise transformation. Currently serving as Executive Director at BGR Neo Limited. He leads automation and digital transformation initiatives to drive innovation and sustainable industrial growth. Previously, as Head Automation, IoT, and Industry 4.0 at Tata Electronics, he led the implementation of advanced smart manufacturing and digital factory solutions at scale. His professional journey includes leadership roles in reputed organizations such as Tata Electronics, Titan Engineering and Automation, Tech Mahindra, Beckhoff Automation, Satyam, and Vent India. His areas of expertise encompasses industrial automation, robotics, machine vision, manufacturing execution systems, industrial IoT, product development and innovation management, and global program leadership. Mr. Nana Prakash holds a bachelor degree in electronics and communication engineering and an MBA in project management. He is also a certified independent director from both IIM Bangalore and Indian Institute of Corporate Affairs. With a unique blend of technical expertise, strategic vision, and leadership excellence, he continues to contribute significantly to the advancement of digital manufacturing and industrial transformation. So with this brief introduction, let me once again welcome a resource person of this first session, Mr. Nana Prakash, who is the Executive Director on behalf of Department of Mechanical Engineering, organizing team of Knowledge Institute of Technology. Over to you, sir.
Thank you. Thank you very much for the opportunity given to me to present to the team of professors. I would like to thank Knowledge Institute of Technology and Mr. Sanmugam, my mentor, who has been working with us in few decades of my experience. And thank you. Should I start the presentation, sharing the presentation, and we'll start?
Yes, sir. We'll go ahead.
I'll switch off my video for better bandwidth.
Yes, sir.
Hope my screen is visible to you all.
Yes, sir. We are able to see the first slide, sir. Industry 4.0 and Smart Machine Architecture.
Yeah. So very good morning to all. I would like to start with the Industry 4.0 and Smart Machines Architecture. What I mean is what it does mean for us is it's innovative automation and transforming manufacturing processes, which leads to Industry 4.0 as a stepping stone. So the session I'm going to cover on few topics, what is the industry evolution and Industry 4.0 and cyber physical systems, smart machines, industrial IoT, Internet of Things, and OT about network security and digital twin, and some few used cases what I have come across and what is the best fit for industrial IoT, and a few of my thoughts around academic and industrial integration about Industry 4.0. You can very well stop me in between, or I have a questions session at the end. We can discuss a lot about it. On the flow, when you want to have any questions, please stop me. We can discuss and then move on. Hope this is fine, right?
Yes, sir. We'll go ahead, sir.
So, as you all aware, industrial revolutions, we talk about 1.0, 2.0, 3.0, and now it becomes 5.0. It all started from mechanization to the human-centric intelligence. That's what we are in today. And it was like machines doing work to the machines understanding the work and the machines working with humans. That's where we live today as we speak in 2026. That we are, our revolution started in 1780 actually with 1.0, where it used water power and steam power for machines to work. Then there is a mass production and electricity came in, and there were few assembly lines which was manually operated, which was the Industrial Revolution 2. It's 1900. And in the Industrial Revolution 3, which we have used the computer and a few automation solutions in 1970s. And then in 2000, we had come across the internet and cyber physical systems. And in India, basically, I have seen we are largely living in between industry 3.0 and 4.0. Majority of the manufacturing industries we are in. We still have not completely adapted industry 4.0 in all manufacturing segments. We are evolving and we are growing. Whereas in my experience, I could see in Europe, uh, uh, they have much better equipped and they have transforming towards Industry 5.0 very much. In US as well, to some extent. And in China, definitely far ahead of us, and they have been moving beyond Industry 5.0, which is lights off factory. There is no man in the manufacturing system. That's where they are moving in. So with this revolution, we have now, what is Industry 4.0? According to my view, Industry 4.0 and across the world, what we talk about, it talks about Internet of Things, and it uses the simulation, it uses the additive manufacturing, and where you all might have come across some of the uh, 3D printing and lightweight components used in manufacturing or for machineries and for aerospace industries. And then there is a cloud computing about, and there is a augmented reality. Now it's called as mixed reality, where augmented reality and virtual reality has been combined and started working on now. And about cyber security, which is an important topic in Industry 4.0. And then there is about the big data and data analytics, and about the robots, which is a robot, cobot, and autonomous robots. And all we talk on the Industry 4.0 using these technologies, a system integration plays a major role to finally make it work, and then which is going to be meaningful and useful for manufacturing industries. So it's about industrial IoT. It's called as, this is a physical machinery, sensors and devices which is connected to a network to gather and share the real-time data. That's what about in the industrial Internet of Things. And artificial intelligence and machine learning is about algorithms that analyze the data to identify the patterns and optimize the production schedules and predict the maintenance needs before machines break down. Where the machine breakdown analysis, predictive maintenance schedules are all, uh, developed using AI and ML algorithms. For that, the basic data required is the physical machinery, sensors, and devices. And then it's about cloud computing, centralized data storage that allows the factory managers monitor, control everything in real time and every event remotely. When we talk about the factory, it's about a production facility situated in one place or multiple locations and various product ranges of like when you talk about automotive, they produce cars in one location, trucks in other location, and other types of vehicles in different locations. So the data storage is a centralized which helps them to monitor and control in a real time. What is the production plan versus actual? What is where it is a bottleneck going on now, and how easily the supply chains can be rerouted according to the market need. Everything is based on the cloud data storage. And then we talked about autonomous robots and cobots, which is smart and collaborative robots. It performs a complex task, and it also cobots can work alongside of the human operators. And the big data analytics comes alongside with the cloud computing, and also it uses the AI and ML algorithms where the massive set of data and which is going to balance the supply chain demands and also going to reduce the waste. This is the majorly it is used in Industry 4.0. And the critical part in the Industry 4.0 is the cyber physical system. And what is cyber physical system? Cyber physical system consists of remote diagnosis and remote services, and it can have a remote control, condition monitoring. It can monitor the system health and also the structural health of a machinery and equipments. And the major thing is on the production plant, the track and trace plays an important role where the parts produced. For example, I have been actively working on a project in mobile manufacturing where we need to necessarily monitor the product from the raw material till the delivery, and also it comes back after market. Once it is sold, when there is a defect, it comes back to us with the particular traceability, and then we will trace back where exactly and what machines it has been produced so that we find a root cause and able to solve it. So these are all possible with the cyber physical systems, and which is connected through network, and also it is monitored and analyzed. So now the cyber physical system is evolving. There is a new potential across industry is growing where there is a remote work management. If you see industry today, and then during COVID situation as well, you might have seen lot of remote work we have done, work from home and other things, where the people not necessarily be in place, and how the work can be tracked and how the work can be managed to produce. Where there is a physical manufacturing done, of course there is no choice, we need to be there. Whereas other works can be remotely managed. And the monitoring and diagnosis. Uh, the monitoring and diagnosis is an important, factor where the multiple uh, production lines. Some of the manufacturing where they set up a production line separate and final assembly, testing, and delivery to the customers as a separate locations they will manage. That is due to geographical presence to make it easy for the supply chain. And second one is due to the like economic factor, like some of the, for example, Andhra or some other state is giving a better, I mean, the tax structure where it is better to assemble and sell there. So we will save money on that. So the economic reason, some of the customers or some of the manufacturing uh, plants will set up assembly and testing, where they will have a different sub-assemblies in one location and final assembly in one location. There it plays a monitoring and diagnosing of the final testing and the status of the production is very much important. I talked about within India, it also has today and majorly in automotive I have seen in various countries they produce and send it to different countries for assembly and testing and delivery. So that as a small kits they assemble and deliver it to the final assembly line and they will deliver. So this is one of the experience I have. I can say in track and trace and monitoring and diagnosis, which I we have worked in one of the project in BMW in India. I have seen the production happened in Germany, Thailand, and Indonesia. Four different countries the product comes and which comes with the own barcode system. And in India, they have to again combine those four products and finally assemble and deliver. So where they have faced a lot of issues in terms of traceability, which these traceability systems installed by us in India, and then it helped them a lot of tracking. So it helped them in terms of identifying the issues and solving the production line problems in India very quickly. And then the new potential in the services and processes. When we talk about services, it is about after market services. So you can see a lot of automotive vehicles today, it has come a lot of electronics built in. Right? Earlier vehicles were in mechanical based. So where you need to rely on most of the mechanical systems which can be serviced by one or the other technicians. Most of you might have faced the new cars when you give it service. When there is an electrical problem, they take time. They don't find the right technician to analyze and solve. So those cases today it is remotely diagnosed and then it is getting solved wherever the service people available across globe. They connect remotely and get this service done delivered. So this is the potential implications are going to come with the impact of Industry 4.0. So it's all about merging a physical and industrial assets with the digital technologies like IoT and cyber physical system. And it's a real-time decision making. It enables the real-time decisions through connectivity and interaction between machines, humans, and software. And it's also about the proactive maintenance and optimization. And the next topic I'm going to talk about on the smart machines. What is smart machines? Any idea? Any of you have any idea about smart machines? Can I hear someone off from you? Hello, am I audible?
Yes, sir.
Can anyone tell about what you think about smart machines?
Sir, it is relevant with IoT
Okay.
and based on the principles of that IoT, the smart machines also interconnected and will work like that.
Mm-hmm.
Sir, it is equipped with sensor as well as machine learning.
Okay. So all these few slides I have taken, do you all understand what is that IoT and industrial IoT? I want to make this session little live as well. So that's why I'm asking some questions. If you are not able, if you are not getting it, I will tell you what is IoT and what is industrial IoT. But I just want to hear from some of you.
So smart devices, it is connected with internet. It will be called as IoT. I hope so.
Okay. What is industrial IoT? I just a few last slide I have told about industrial IoT.
It is focused on manufacturing as well as industrial things.
Okay. Okay, thank you. IoT is commonly called as Internet of Things, right? So the things, whatever you are seeing and in a real world of day-to-day activities, like for example, you might have seen the machines operating through internet, like a washing machine. Today, I can switch on and off through internet from my mobile, right? That's a simple example of a IoT. Whereas industrial IoT is talk about not not necessarily through internet. It can be also a intranet, right? Intranet is nothing but a network within the company itself. Whereas it talks more about the connecting, collecting, and connecting the machineries, connecting the sensors, collecting the data, and using the data and representing the data in a meaningful way. That's all about industrial IoT, right? And the smart machines is about the same. We call it as smart machines because smart machines will have a combined of some sensors and it will have a connectivity and intelligence to operate beyond a fixed logic and a manual input. Right? Machinery can operate in a defined logic and in a manual input. Say operator press the start button, it is going to start and work on a defined logic. Whereas a smart machines is going to be operating in a beyond logic, fixed logic, right? So, for example, smart machines has a sensor which has a position detection and a temperature detection. We can put a logic, okay, upon identifying position 1, then you go to the position 2 and then check for a temperature. What is the temperature? And then stop it. That's the logic we can write. And it is going to operate in the exactly same way any number of times. Whereas when there is a smart machine, when it is called, say the temperature sensor, I am connecting it, making it as a logic, making it as a algorithm, and then as a closed loop when I connect back to the position 2. When the temperature reaches X, then go to position 2, or when the temperature reaches X plus 10, go to position 3, and I can use various logics to multiple operate in different positions. That's about smart machines, right? Hope is that clear for you?
Yes, sir.
Yeah. And the core features is about condition monitoring, adaptive control, integration with systems like DCS and SCADA. So hope you are aware about DCS and SCADA. So SCADA is about supervisory control and data acquisition. It uses largely in manufacturing industries and in process industries. Okay. SCADA mostly works with the descriptive inputs and then deterministic inputs like digital IOs it covers majorly, and it is going to represent the state of a machine. whereas distributed control system is widely used in process industries where it continuously monitor the process variables and it is going to uh, take the sensor data and uses the SCADA to represent. Okay. And what is the benefits of smart machines? Smart machines is going to benefit in terms of predictive maintenance, reducing the downtime and improve energy efficiency and in high load systems like it's about load balancing, energy efficiency, overall uh, idle. If the some of the actuators and some of the motors are not running for few minutes, then it can switch off on its own and then it can restart, which is going to save a lot. These are all the benefits of smart machines. And the role in Industry 4.0 is as a intelligent nodes. All these smart machines are going to act as a intelligent nodes, providing a real-time insights for anomaly detection and optimized performance. There are two aspects here. One is anomaly detection. Second one is optimized performance. So, what is anomaly detection? What is optimized performance? Any idea?
No, sir.
So, the anomaly detection is about I have defined some machine logic. It has to operate in that fashion, right? When there are so many sensors and actuators are connected to a machine and it is supposed to perform on certain logical sequence. And when it is going to continuously do, right? When it is not performing in that logical sequence, there is something is stopping for the machine, right? Then it has to immediately detect and inform to the controller or the control system to stop the machine or to intimate the machine operator or the supervisor or the manager according to depends on the anomaly, right? So this is with respect to the algorithms what is written on the machine. It knows what is the regular sequence and if it is not coming within those preferred timing or preferred logic, some sensors are supposed to come within 10 minutes or whatever it is. Just for example, I'm telling. If some sensor is not coming in 10 minutes, then it is going to indicate that it is some anomaly is detected. This is with respect to time. Whereas with respect to logic, say that I have connected 10 sensors, I have defined the logic 1, 2, 5, 6, 10. Okay. If instead of 1, 2, 5, 6, 10, if it comes 1, 2, 6, 5, 10, it is also an anomaly. Then it is going to detect and tell me, right? This is the anomaly detection. And the optimized performance is what is meaning here is the when the performance is about one is about the energy performance, right? Optimize on the energy, then optimization on the time as well, then optimization on the productivity, optimization on the quality aspects. So these are all called optimized performance. Okay. Is this clear for you? Any
Yes, sir.
questions? Any questions from anybody else?
Dear participants, if you have any questions, please post in your chat box, please.
So the typical smart machines, it is called as factory of future. The photo what you see here is what made for customers. Here you can see this particular setup has consist of it is programmed for using robots and conveyors and several of sensors and camera elements to it. And the factory of future, it means what it means is it has to take care of the predictability aspects and it has to take care of quality aspects. It has to take care of enterprise application integration, which what does it mean? It is enterprise application is about the production schedules, which is planning from the sales. The production targets are given, and then it has come. It has to come into the supply chain internally within the manufacturing, and after manufacturing, it has to reach back to customer, and then everybody should know the information. What is my product, where is my product, and when it is going to deliver, when it is going to ready for me. That is what application integration. And everything is called, I have to see, right? That is called visualization, right? It helps shorter time to market, and it helps by simulating the factory scenarios in lab, and taking it back to the factory for their implementation. So in turn, it is helping customers to accelerate their execution. So the factory of future is the lab setup is what we try to replicate from the factory scenario to make it work before we actual production does. Okay. The smart machine architecture will have a physical layer. The physical layer includes the machine's sensors and actuators that collect virtual operational data like temperature and vibration. It's not only temperature and vibration, it is also has a lot of other parameters, we can say noise, distance, color, uh, speed. A lot of parameters are there. We can take any type of inputs. And next layer is the control layer. Bottom layer is physical layer. The next layer is the control layer, where it predominantly operated by PLCs, DCS, and it will execute the safety logic and automation in automation, which is essential for the real-time operations. The next layer is the edge layer. Edge layer is the computing platform. It's like a small computer, we can say, where it performs a localized data processing, where the raw data signals are getting filtered, and the event detections are monitored. And then there are some local decisions where the deterministic signals are going to get collected, and decisions are taken in the edge layer only, without going to depending on the cloud. Because when we talk about cloud or centralized server, it has the certain critical signals in terms of microseconds or milliseconds. We have to take a decision as and when I detect the event. It has to happen in the edge, because by the time it hit the cloud and then comes back, it is going to be milliseconds, or sometimes it delays, depends on the bandwidth, what is the internet bandwidth and everything. So the deterministic layer is bound to get solved in the edge layer itself. And of course, the next layer is the platform and cloud analytics. The cloud layer enables the centralized monitoring, as we discussed earlier, and it involves digital twins to some extent. I will cover in a digital twin in a separate slide. And the key performance information tracking and advanced analytics for optimal performance. As you can see the typical architecture here. This is the Industry 4.0 architecture. Whatever we discussed is represented in terms of a single picture. You can see the bottom layer, factory 1, 2, 3 is the control physical layer. And then next layer, what we discussed, control layer, edge layer, right? Control layer is about next layer, plant network, logistics solution and everything. The enterprise integration we talked about, that is the next layer. And you can see on the left side is the suppliers network, which is getting connected to the supply chain. And on the right side, you can see the customers, which is connected through aftermarket service, warranty. They are connected to the enterprise. This is how a typical manufacturing industry is getting connected. Does this make sense for you? Any of you able to see this diagram and any questions on this diagram? Please raise your hand or type on the comments. Hello.
Yes, sir. No questions from the participants, sir.
Okay.
Please, sir, you can.
So on the IoT value chain, what is the IoT we discussed? The entire value chains, it flows from devices and it flows on the communication side, and there is a storage and there is a applications and analytics. Okay. So the physical layer is called sensors and gateways are called as physical layer. And what is sensors? Sensors, it can be two ways. One is you can design and develop your own sensor for a particular application, or there is a COTS sensor that is commercially off the shelf available sensors and integrate it. Right? These are two types of sensors. And gateways, what is the gateways? We can develop our own gateway hardware and software. Firmware, it is called as firmware and software as well. And gateway consists of protocols MQTT, HTTPS, TCP/IP, and UDP. And it will have its own operating system. It can be either Linux, Windows, or Windows CE, or anything, any of the OS. And there are commercially off-the-shelf gateways also available, which can be used. And the next platform layer is consists of cloud, storage, and visualization and data analytics. So what is the cloud? Cloud, you must have come across AWS, Azure, and Google, right? Now also there are a lot of private clouds available beyond this. And the storage is about data migration. Whatever the collected data from the physical layer has to be stored here in a cloud storage or a server. Then on the visualization front we talk about KPIs, key performance indicators, dashboards and reports. And also it is about enterprise application integration and how we manage the big data, and the visualization also part of mobility application. Like in mobile, visualization is different from the computer. Mobile or tab or any other application development is called about mobility applications on the visualization front. Analytics is about a predictive analytics and a rule-based algorithms. These are all will be used to construct this end-to-end IoT value chain. Okay. Any questions? I want some interaction here, please, because I have not come across only speech for 1 hour. I want some questions and clarifications so that we can be live and interactive.
Sir, one of the participants is asked about reliability of the edge layer intelligence.
Reliability of the edge layer intelligence. Edge computing, edge servers are available in various formats. It can work in a physical manufacturing floor under extreme temperature or extreme weather conditions. There is a protection available with IP65, 69. So it is extremely reliable and it can be used across all industries. Right? Is that answers for you?
Yes, sir. Okay, sir.
What is that? Machines connected to IoT. Breakdown is about to happen. Optimize performance. So all only. Okay, sir. I didn't see any much questions. Okay, next important topic about the security aspects. OT. What do you mean by OT? Anybody answer? What is OT? If you are not speaking, at least you can answer in the chat. Operation downtime, no. OT it is. Anybody else try? What is IT? Anybody else can answer for IT? Yeah, Prithviraj, I think you are right in IT. So it is information technology is IT. Operations technology is OT, right? So operational technology is about more on the manufacturing operations. Information technology more on the office environment where we sit in office or in colleges where you work, you connect through your laptops or computers through your network is on the IT side. OT side has a lot of kind of restrictions we have to bring. Otherwise, what happens if somebody, you can see in my presentation, if somebody comes and hacks to your network in your manufacturing network, what happens? One of the example you can see operational downtime. German steel mill suffered a massive damage following a cyber attack. So they enter into your network and damage your communication. So what will happen? The machines will not perform as intended, and then eventually it stops. Right. Another one information on the product manipulation. Fired system admin at a paper factory caused 1.1 million lost or spoiled production. Okay. So they manipulate. You ask them to produce a A4 size paper and it produces A3 size. What will happen? It is not going to be a desired output, right? So that's what happened in 2017. And there is a sensitive information theft in a pharmaceutical organization in 2014. And there is a ransomware attack, which in Honda plant, there are 1,000 units were not produced as planned. So these are all the typical impact when the security is elapses on the OT side. Okay. So in turn, if there is no security, we see the loss of revenue, loss of competitive edge, and we see the reputation damage, and we see the regulatory intervention. The regulatory also will come into picture when you are attacked, and then they will analyze what kind of systems and implementations you have done, which you have not done, where is the gap, and it is going to call for a massive investment across your factories, and it is going to be a restructuring of your factory. Okay. A typical OT operations technology, what I talked about is here. You can see the network layer in the control network. 1 and 2 you can see, right, where the PLC is are connected on the shop floor. And then I have also marked some brown color round one, which is the integration points. I'll talk about it a little later. You can see there is a network layer 1 and 2, and there is a supervisory network layer, which is on the shop floor where it operates for production. where maintenance workstations, engineering workstations, HMIs, SCADA, everything is connected. Then there is a command and control center where there is a overall manufacturing data it resides, right? Which is the uh, servers. It can be a file server, it can be a data server or historian server, whatever it is. Then there is a switches, backbone switches on the right side. Then there is an industrial gateway. And then there is an enterprise network. This enterprise network is what I talked about, IT, information technology. Then it goes to internet and gateway and internet. Okay. So this is left side, what you see is the OT layer and the enterprise network is the IT, which there is a bridge between that is the industrial gateway. Now I come to the monitoring part of network, which is the integration point, right? Monitor and the network changes by detecting the new devices, traffic patterns, and protocols. These integration points it is monitored for any of the new devices. For example, when I plug a new PLC, suddenly it immediately detects and it detects the traffic patterns and protocols, what it is communicating. Then there is a real-time detection of cyber attacks and non-malicious threats. It is going to detect the cyber attacks and non-malicious threats. And it's also going to manage the risks and predictive alerts to improve security and resiliency of the production environment. This is what it is going to do on the network side monitoring. Okay. This is very important topic when cyber security and networking, network security on the industry 4.0. Okay. Any questions here?
No, sir.
So next one is on the digital twin concept. I see this is a big topic, digital twin as such. We can take another half an hour separate topic as well. So, but I just want to cover the basics of here. If you want, I can take it in a separate session. We can do. Digital twin is a real-time representation of a virtual. The virtual, you can see the left side diagram, some robots operating and some machines are getting assembled and robots are helping to produce those machines, right? It's a virtual model what we have developed before even we actually implement. So it's a simulation of the real environment is called digital twin. Okay. The physical industrial assets like boilers and turbines and robots and manufacturing, it has come up now and we are widely using on robots and other machinery simulations. And we can also predict through digital twin any anomaly detection. Anomaly detection here, what it means is suppose I have to pick and place using a robo within a 10-meter distance, whether am I able to pick and place or is there going to be beyond 10 meters going or less than 10 meters it is going. The boundaries, is it reaching within the boundaries or going to be detected in the virtual environment itself. And we will also predict the lifetime estimation on the using the simulation itself. And we can also do the process optimization. Like for example, I place the robot here. Why? I can place the robot on the backside of the machine, or I can place the robot on the top of the machine or sideways of the machine. So this is called the optimization of the cycle time. So which place I place a robot, I place a machine, how much cycle time, how quickly I can produce is optimization. And how can I easily approach the machine when there is a downtime. And also we need to take care of the safety. You can see the yellow marked fences placed here, how the safety is maintained over there. So everything I will not go ahead in real and understand the problem, whereas we will virtually simulate and understand the problem, then we go for real manufacturing. This is called digital twin. And it's widely used in thermal plant, process industries, and manufacturing industries, and which helps to test scenarios and support industrial education. Maybe in your college also you must be having some simulation tool. I'm not sure, which is going to really help for the students. Okay. Now, after the digital twin, I'm going to go for some few of the use cases. Okay. For example, one use case is the thermal power plant. The scope of the work is like monitor and control the thermal power plant. It does look simple, right? What can be the Industry 4.0 solution? The solution highlights are here. Predictive maintenance. We discussed early detection of turbine, bearing, wear, and pump cavitation through vibration and acoustic analysis. Improves variability. Does that make sense for you? What we discussed on the theory versus what practically it is implemented? Does that make any sense for you now, able to connect with the real use cases? I'm asking. Hello. I'm asking the participants, please. Thanks, Mr. Dhanabal. I have only one. Yes, Prakash, thank you. Prithviraj, thank you. What is that, Dhanabal? Optimization of performance. Yes, of course. Predictive maintenance is to optimize the performance. Then we did boiler optimization. Digital sensors and AI enhance the combustion efficiency, reduce heat rate, and lower emissions in boiler. Then the real-time monitoring. Continuous monitoring of cooling pumps, fans, and condensers minimizes the auxiliary power use and operational costs. Okay. Prakash, implementation cost of digital twin is varies, depends on what digital twin you are trying to make. For example, the robotic based simulation tools are available, and it depends on the software what we use. The cost differs, and also a time which spent by both manufacturing team and the design and the tools. Whoever is going to work on the simulation tool. It varies. It cannot be a single cost, right? Minimum network bandwidth requirements for what? Dhanabal, can you be specific? Cyber security risks in digital twin possible? Yes, possible. See, the digital twin network bandwidth is something, it's not about network bandwidth, it is about system requirements. What I use on the computer, which should have a more capacity, RAM, and then storage capacity, where I can build, I can see the simulation, how effectively it is operating, right? Because always the bandwidth, it is connecting to the manufacturing plant versus to my digital twin. So how quickly it is updating the data, that's where the bandwidth, right? Whatever we operate through internet, it's about we are limited to the bandwidth of what we have. Like if some places 4G is available, that is the bandwidth. Some places 3G is available, that is the bandwidth. And we are yet to see 5G here. Okay. So these use cases, I am talking about not only the digital twin, it is about more on the IoT, Industry 4.0 as well. Okay. Major challenge in implementing digital twin technology in manufacturing. Sir, in manufacturing, the major challenge is not able to create all the manufacturing scenarios in a, virtual model. There is softwares available for predominantly Siemens and some of the German guys are having the software. The challenge is making available of the software at the cost of what manufacturing plant need here. We need at low cost, we need at minimal cost. But those softwares are not so easily available at less cost. That is one challenge. Second challenge is on the putting the virtual elements into the, sorry, real elements to the virtual elements, right? Now, creating all types of process or manufacturing environment into a virtual world is going to take consume a lot of time and energy for us, and which by the time our manufacturing plant has to be set up. For example, I have to set up a manufacturing plant in 6 months to 1 year. I have to spend 6 months of virtual time prior to building the physical manufacturing plant. That is the time it takes. Okay. So then on the edge analytics and dashboards, centralized dashboards and edge analytics empower engineers to analyze KPIs, schedule maintenance effectively. This is what on the thermal power plant case. Okay. Next, industrial equipment. Build and what is the scope of that? It's on the industrial platform. He'll build and host complete end-to-end solution to offer rotating equipment health monitoring solution. Here we have done a design and development of a communication device with the rotary equipment enabling real-time remote equipment health monitoring and identifying a anomaly in its routine working. So it has been about it's about development of a vibration sensor and a gateway, which we discussed earlier, a sensor gateway and a firmware is using a 6-LoWPAN and Wi-Fi to push data to the cloud after performing the edge analytics. So the vibration data is analyzed on the edge and data is pushed through Wi-Fi for doing for doing further analysis. So vibration-based predictive analysis, transmitter and receiver design using RF signals, and development of algorithm for detection of the passive tag. Okay. So rotating equipment will have a tag, whereas the receiver will have a through RF signal, we will receive the data and then analyze within the edge and then push the data to the cloud. That is the use case. And in solar power plant, there is another use case. Configure remote monitor and control geographically distributed solar power panels. So it is distributed across the various locations. So we diagnose the performance issues of PV plant, optimize the farm operations and maintenance, panel cleaning schedules, long-term reliability and mean time before failure we have monitored, and it has been audited and report has been produced on the energy production. That's it. Another use case. And there are another 6 examples which I am going to give you where how manufacturers are using the IoT for business. These use cases are going to be representing the practical on-ground implementation using whatever we discussed, big data analytics and automation technologies. One is on the rapid costing. Many industries, you can see the functions are internal functions like suppliers to product management group to the sales team, and they provide cost estimate, end-to-end business development. They have to do it internally. There is a market dynamic also, which requires a costing based on price indications about a particular piece of equipment. There has to be a quick turnaround for is the main factor for enterprise to win or lose orders. So market based on the market scenario, they have to fix the price quickly. And historical data, including hit rates, customer performances, footprint requirement, earlier tender records, executed projects, and the product variations that has to be combined and analyzed and then given a right quality for a new tender. That is one of the real-time example. Then NCR analytics, non-conformance report analytics. Many manufacturing organizations collect data points, non-conforming events when a product process does not comply with the standards, right? It's a tool to reduce errors and uh, and it is also stop the faulty products reaching to the customers. So IoT technologies help the NCR data find relationship between the NCRs and support prediction for future non-conformances. Plant load optimization. So this is about supply chain from sales receipt till the delivery. It can analyze on the supply chain day-to-day operations how it can meet, and also it can analyze and forecast about the financial performance whatever the decision has been made. For example, today a product type A has to be manufactured or B has to be manufactured or type C has to be manufactured can be determined basis the supply chain availability and the financial conditions at that point of day or time. That is another example. Then the operational improvements, shop floor operational improvements. When it comes to that, for example, the critical machine tools are designed to operate within certain temperature and vibration ranges. Sensors can actively monitor and send alert when the tool deviates from the prescribed parameters and preventing the malfunctions. So this is helped big data. This analysis is going to help improve overall equipment efficiency. And there is another use case on the suppliers and supply chain about. There is another use case on the health, safety and environment. These are all the use cases which is very much implemented in the industrial IoT. Okay. KPIs for typical industrial equipment. Key performance indicator is the OEE, downtime, and cycle time, tag time. These are all the critical KPIs for the industrial equipments. Okay, now what is the academic and research relevant? This is according to me. I put what it can. On the curriculum integration, Industry 4.0 concepts can integrate with the mechanical engineering subjects like thermal engineering and mechatronics to enhance the learning. This is one of the thought I had. Second one is interdisciplinary research. Like research opportunities include cyber physical systems, predictive maintenance, algorithms, and edge analytics in industrial context, right? What is the industrial context? So why interdisciplinary? Mechanical stream can do stress analysis, kinematics, and structural health. Electrical can work on power management, smart actuators, and signal processing. Software stream can work on cyber security, cloud architecture, and database management. If interdisciplinary research combining these three can help to achieve a Industry 4.0 kind of Industry 4.0 understanding and a good project for the academic students. Any thoughts on this? Whatever I have mentioned here, does it make sense for you? Hello.
Yes, sir.
So the next is on the academic industry alignment. Always hands-on applications and case studies prepare the graduates for AI-driven roles and in modern industrial environment, right? And bridging the theory and practice. Connecting academic theory with industrial application creates a meaningful student learning and a stronger partnerships. Okay. I've also put some thought on the theory and practical applications. What are all the theoretical frameworks which is widely used that focuses on mathematical, architectural, and conceptual models which governs the smart systems, right? One is the system architecture models. We call it as reference architecture model Industry 4.0, breaking down assets into layers, which you have seen. I have presented one of the architecture, right? That's a kind of a reference architecture for Industry 4.0. Then there is about a 5C architecture on when it comes to cyber physical systems. It's about connection, conversion, cyber cognition, and configuration. That's called cyber physical system. And then on the in the ISO and IEC standards, there are formal models for interoperability, data management, and cloud integration. And then optimization and predictive algorithm side, right? Markov decision making process, modeling autonomous decision making and machine self optimization. And then Bayesian network, creating probabilitics frameworks for diagnostic reasoning and uncertainty. Degradation physics, combining physical stress models with data-driven machine learning. These are all things used while we develop the digital twin or the network monitoring, which I talked about, and anomaly detection we talked about, right? These are all the algorithms are getting used there. So, which is a theoretical framework where the students can definitely learn and understand in depth on this. And about network security, when we talked about, it's about graph theory, analyzing a decentralized machine-to-machine communication topologies, modeling cyber attack scenarios to design resilient defense frameworks, control theory, developing distributed control loops for multi-agent system ability. Okay. And on the student project, which helps the practical applications, where focus on engineering implementations, hardware integration, and measurable soft floor outcomes. What I think is on the condition monitoring and maintenance, vibration analysis, mounting and accelerometers on a CNC spindles to predict bearing failures, thermal imaging, tracking heat dissipation on motors to prevent critical overheating, edge employments, deploying a lightweight Python, C++, ML models directly onto the microcontrollers. Digital twin, a CAD integration, connecting a live PLC data text to a 3D CAD models via MQTT, which is a very much possible project. Virtual commissioning, testing a PLC code on a simulated environment before physically built. Mixed reality, we talked about augmented reality and virtual reality. This is a mixed reality using AR glasses to overlay live telemetry onto physical machine components. And on the smart production control, automated sorting using computer vision on conveyor belts for real-time quality control. Adaptive machining, adjust feed rates dynamically based on the real-time tool wear data. AGV fleet management, deploying an automated guided vehicle that dynamically reroute around obstacles. Does that make sense? I think this is going to be my last slide. I have put a lot of thoughts around this slide and I would like to hear from you on this. Is there any questions? We can take it up.
Sir, is it possible to implement old equipment to IIoT platforms, sir?
Any questions? Does
Sir,
my
is it
previous
possible?
slide is okay, making sense? Am I audible? Hello.
Yes, sir, it is audible, sir.
Hello, am I audible?
Yes, sir, it is audible, sir.
I'm not able to hear any one of you.
Sir, is it audible, sir? I'm able to hear your voice.
Sir, it is audible only.
Yes, sir. Yes, sir. You are audible, sir. Sir, you are audible, sir.
Yes, sir.
Sir, one question is raised against in the okay. Prakash, you can raise a question.
Is it possible
Sir,
to
is it
implement
possible?
old equipment to IoT platforms? Yes, of course. We need to change a lot of items like sensors and some of the few items. It depends. We can do. Major industries prominently uses IoT. IoT is used now across all industries like uh, like mobile manufacturing, electronic industries, automotive industries, and pharma, food and food technology, FMCG, and like white goods manufacturing, AC. A lot of manufacturing industries uses. Okay.
Participants, if you have any queries or doubts that you want to be clarified with the resource person, you can raise your questions. Otherwise, you type your queries in the chat box.
Kindly tell about IoT and IoT data storage. See, IoT and IoT data storage, there is a kind of, majorly IoT data storage, uh, the local storage will be less, whereas the cloud storage will be major in IoT, whereas IIoT, it's some local edge storage will be more and edge analytics will be more than cloud storage and analytics. Okay, Prakash?
Yes, sir, thank you, sir.
Done, sir. Any other questions? I want to hear a lot about on my this last slide. Really, does that make sense for your student projects and my theoretical frameworks? Which you can exercise or you can do. I want to hear from you. about this last slide. Again, I'm presenting to you.
Yes, sir. We can do exercise for digital twin implementation, sir, to our students' projects.
Okay. Why not condition monitoring? Why not smart production control? Is there any challenge?
Sir, these are all quite interesting. We'll take up, sir. We'll look into and we'll take up further, sir.
Okay, okay.
Thank you for sharing this such a problem-based learning approaches. Looks very excellent, sir. We'll take up, sir. We have
Okay.
9 UG programs in our institution. Collaboratively, we can, and I think we can approach it towards this.
Okay. Okay.
We'll go ahead, sir. Sure. This will be highly helpful for our students to improve their, to bridge their academic and industrial needs.
Okay, sir. Thank you.
Very beautiful, sir.
Thank you, sir. If there is no other questions, then I would like to thank you all for this opportunity and for your attention for this entire session.
Thank you, sir. HOD, sir, would you like to make any comment on this session?
Oh, go ahead. Sir, we personally thank you, sir, for making your kind efforts to being present in this day one, the first session. Normally, being the first session, it's quite challenging. So, the way you have prepared your content and everything on I 4.0 is really amazing. And hope this contents are been very well received by all the participants. And moreover, we are recording the same, and it will be available in the Knowledge System Technology website too for all reference in the future. So it will be gone through by all the faculty team of our institution too. So in such a way, your session is very highly helpful towards making this industry gap bridging. Thank you so much, sir, for your great support and enthusiastic presentation on this fine morning.
Thank you, Prabhakaran sir and
We'll be in
Karthi
touch, sir. Yes.
and the entire professors team. I am privileged to present you with all professors in front of professors. And it goes back to my college days as well, probably, where I would have listened. I don't have an opportunity to listen like this during my study times, but it's been wonderful. Thank you all. Thank you one and all. Thank you, Shanmugam sir, for this arranging this session.
Yeah. Thank you, sir. I'll convey
Thank
the
you,
same
sir.
to them. Yeah. Sir.
Thank you. Thank you.
Thank you so
Thank
much.
you, sir. Thank you for your presentation. And it was really insightful and very informative to all the participants who are joined in this session. Okay, if you have any doubts, then definitely we will get back to you.
Yeah, please.
Okay,
Anytime. I am there to
for designing
clarify.
any syllabus for our own institution.
Very good, sir. Very good.
Thank you, sir. Thank you very
Thank you
much
so much.
for your participation. Thank you, sir.
Sure, sir.
Good afternoon to all. I am Mahendrakumaran from Ashok, Leyland. I am working as a head of testing department in Ashok, Leyland. My experience is about 35 plus years. I've been more onto testing, instrumentation, data acquisition. And in today's session, I would like to bring in my experience from automotive testing world. We will proceed further for the presentation. So today's topic is sensors, instrumentation, and data acquisition. And this I would like to take it like how we automotive engineers use the sensors for our required tasks. It could be like vehicle testing, collection of data, analysis, and further, and so on. So, by the definition, sensors are the devices which are used to detect the physical quantity and convert it into usable signal. When I say signal, it could be of both either analog form or a digital form. And instrumentation is a science which helps us to get the output of the sensors to be converted into usable form. When I say usable form, it could be used by us as a raw data itself for our further analysis, or if the data is meant for some automotive control system or any other machine for a discussion sake, if we take, it is used to convert it into the usual form and give it for the further processing. It could even end up in a command saying that, say, stop the machine, bring the vehicle to halt, and so on. The data acquisition is the process of sampling, measuring, and converting the real world physical phenomena and to put it into use for further processing, or like in vehicles or any other thing, we do use it for giving the required commands. Sensors are there today in everywhere. They are there. If you look at 2 decades back, the number of sensors on a vehicle would be limited to few numbers. Maybe I would say we will have some 7 to 8 sensors which are very critical only to provide information. And most of those sensors which we used on earlier automotives, be it a car or truck or anything, they're very simple ones which just converted the signal and gave it to the required next unit. It could be a conditional amplifier or anything. And in today's life, it is there everywhere. For example, one practical example I would like to show is our mobiles. Almost every one of us today are so health conscious. We all keep a look at how many steps I have made for the day. Now, even the cell phones that we have are equipped with motion sensors. These motion sensors track our number of steps and provide us an input on how many steps we have made. So this is the penetration level of sensors into our day-to-day life. When we have such amount of penetration of sensors into a normal human and day-to-day activity itself, then we can imagine the amount of their penetration into the automotive field or any other field that I have marked here. And today, being an automobile engineer, I will talk more on automotive related sensors, how we instrument them, for what purpose, and how we analyze them or use them, or how we use it to control or to operate our vehicles. So sensors, when we say normally, the conventional sensors, that is what the basic form of the sensor, it all does the work of just converting the physical value into an electric signal. When I say electric signal, it could be usually analog signal in the conventional sensors. But in the smart sensors, they go one step further. They have the sensor and they have the required conditioners and they convert it into the required usable form of the data, and
Excuse me, sir.
on time.
Sir, sorry for the interruption.
Yeah.
Sir, you please share your slide to slideshow mode.
Oh, sorry. It's not visible, huh? Sorry.
Double window is visible, sir. You please pick the 3 dots, sir.
1 minute, 1 minute.
Sir, hide presenter view, sir. Hide presenter view.
Yeah, sorry.
Not an issue, sir.
Is it okay now?
Yes, sir. It is okay now. Thank you, sir. Thank you.
See, I'm new to Zoom here. We normally use Teams. Sorry. So, as I said, the smart sensors, they go one step further. They have the required processing units. Could it be a conditional amplifier or any other form of the equipment which converts it into the usable form of the data, and it is also sometimes used to give commands. That we will be seeing as we start looking at the sensors which are predominantly used in automotive vehicles. For example, I have a accelerator control pedal. It is one device. You can take it as a smart sensor. It takes the input of the engine RPM. It processes the requirement with given some commands, conditions, and it either opens or closes the intake throttle valve of the engine. So this is all about smart sensors, and there are algorithms available to get the desired output of the given smart sensors. So I've just put a comparison between the traditional sensor and smart sensors. The data output is basic, analog or digital in a traditional sensor, but in smart sensor it is rich. It could be a processed data, and finally it can end up in giving a command. The diagnosis is almost nil in a traditional sensor, and in smart sensors they are done at the real time, and it gives the required reporting either as a command or as a data to be processed for further usage. The communication is unidirectional in case of a traditional sensor, and it is bidirectional. Smart sensors are sometimes, or most of the times, they are used for giving the required command to the concerned unit. Scalability, again, you have the benefits of scalability options also. I have just listed few of the smart sensors which are currently on use. Okay. I'm not going to talk on them because they are all very much available in the Google source or any other source we look for. But these are predominantly the sensors used in industry field. Could it be automotive? Could it be production? Could it be medical or anything? Now I will move into the part of the presentation where I'm going to talk about automotive testing, the role of the sensors, how instrumentation is done, and how data acquisition is done, and for what purpose this data acquisition is done. Yeah. So this is a simple schematic layout of a sensor to the final computer. The sensor is a transducer sensor. It could detect anything like physical temperature, motion. It could sense pressure or anything for that matter. And that gets converted into the signal with the help of a signal conditioning amplifier or a signal conditioner simply into an analog form. And this analog form, again, it is fed into an A to D converter, which converts the analog into digital form as shown in the binary format below the computer. And it is again used for processing further analysis. I just put image of some sensors which we normally use. The first one, let us say flow. So when a vehicle is operated, what are the tests normally as an automotive person will be interested to do? Anyone who is buying a product will be interested in its performance. They would be expecting certain basic functions like I need my vehicle to accelerate to this extent. I want to catch a speed of 0 to 100 within some X seconds. This is one requirement. The second requirement, like when I'm applying a brake, how quickly my vehicle stops. This can be in the form of distance and it can be also in the form of time. Now, how much loud is my saloon cabin inside? Let us assume I am buying a luxurious car, and if the ambience inside is noisy, the engine noise or the gearbox noise is all coming into my cabin, will it be a disturbance or not? So what automotive testing professionals we do is we have a list of performance requirements for a given automotive. Could it be a car? Could it be a truck? Or could it be a bus for any reason? So for each and every functional requirement, we have certain tests to be done. For example, when I say acceleration, I can measure and find out what is the acceleration of this given line is. If the acceleration is not to the requirement, then I need to fine tune further to improve the performance of this vehicle. So what all I would need to do, the way I am firing the engine, how much of fuel I am injecting into the engine for the burning of the fuel and producing the required power. In which gear? Should I need to shift the gear? Should I need to accelerate further? Should I need to brake? If I have to brake, what is the condition that it should enable braking? So many such parameters will have to be looked at. If you ask, testing professionals would be interested on any physical parameter on a vehicle, starting from temperature to pressure to torque, force, anything. I have listed almost what required parameters are there for this. And from this data, we sense, we convert it into the required usable form, and we process it further for further refinement of the product. One important sensor which is available here is the strain measurement sensor. The other sensors are all ready-made. For example, if I take a microphone, I have put sound. If I take a microphone, the requirement of the microphone is for measurement of noise. Again, based on the type of the measurement that I'm going to do, I will be choosing the mic. That mic will be either unidirectional mic or an omniversal mic. For example, let us assume I am going to measure the noise that is emitted out of a vehicle when I am standing by the side of the road. The vehicle just passes by me, how much of noise it is emitted. In this case, I will be using a universal mic, which means the mic has sensors, or sensitivity of the mic is such that it takes in all the noise that is coming out of the given free field. It is around sound, the surrounding environment, whatever is available, it pulls in the noise, finds out, give it to the further processing and takes it. If I need to find out from one single source, from one single direction, whether this is the particular component which is creating a noise issue for me. So in such cases, when I need to pin down the source, or when I am looking at detecting the, when I'm detecting the particular issue of a vehicle, I need to choose a different mic. The sensor selection itself, I went into the detail of this one portion alone to show the importance of sensor selection. See, the data acquisition and further processing of the data depends upon how good are we on choosing the sensors, how good are we in instrumentation, and how good are we in converting them into the required form and successfully doing the further analysis. One important sensor out of all these is the strain gauge. Why I am giving importance for this sensor is, you will normally not find this in regular like standard instrument. Here, the advantage of using sensor is this strain sensor is to it facilitates customization. For example, the same strain sensor is used in the force measurement. The load cells do have strain sensors. The pressure gauges, what we use, will have strain sensors. Of course, there are different types of pressure sensors. Like the one is what I said is strain gauge based. There are again piezoelectric based sensors also. But depending upon the usage, range of measurement, other things, one set of sensors use strain gauges also for measuring pressure. And when I need to measure torque, I can use a strain sensor. So the advantage of strain measurement sensor is it facilitates customization. In the next coming slides, we will see some importance of strain gauge sensing and how it can be customized for a requirement. Why I am saying this is, when I have a complex structure here, for the illustrative purpose, they have given a simple beam onto which how the strain gauging is done. But in real world, the component will be of complex structures. And when the complex structure is there, sensing or calculating. Sensing is a challenge first. Second thing is calculating the required stresses. Even after doing the finite elements model, when somebody is doubtful, he needs to confirm it, they go for this strain measurement sensors. Now I have illustrated few of the samples of strain gauges. Number one is a simple linear strain gauge. This linear simple strain gauge does the function of measuring the strain on the area which is pasted. For example, I have a parent beam as I have shown here. There is a simple beam on a material. If I am putting a sensor in this, and let us assume the forces are acting towards the tensile direction like this. This simple sensor could give me the tensile strength on tensile strain on the given member. Now let us assume how practically this can be put into the place. For example, I have a long chassis frame on a vehicle where I have located some few strain or stress razor points as given by my finite element analysis results. I still want to confirm, then what I do is I paste the strain gauge sensor exactly at the given location on the frame member. Then I try to measure what is the strain. Once I measure the strain, then I have the advantage of converting it into the required signal and use it for further fatigue life prediction. What normally, when you are dealing with a complex structure, what people will do is they will do a finite element analysis. This process in Ashok Leyland, normally we call it as a verification process. When the verification process highlights out that there are certain high-rise stress points or high-rise strain points, we take those locations based on the given directions by the FEA results. We fix the strain gauges in those locations and measure what is the strain. This measured strain value is converted into a time domain history. I will talk about the time domain history as we proceed further. These are these real world operation of this strain gauge with proper wiring and everything collects the time history of the operation and provides us for further analysis. What we will be doing is once I choose the location, once I complete the instrumentation, we will be taking it onto the different routes to look at the different load cases. Whether I should do it in an unladen case, whether I should do it in a laden case, or whether I should do overload, because there are some customers who overload the vehicle also. The member should withstand that also. So what we do is we choose the load cases, we operate the vehicle, take the data, then analyze the data, look at whether the given member is within the given stress or strain limits which is allowed. That is a bigger part of the analysis, and it happens automatically with the help of softwares and other things. Now I will come back to the sensing and instrumentation part. The first example, number one, is providing a visual image of a simple beam onto which a strain gauge is fixed, which captures the strain in which captures the which captures the strain in the tensile direction. Now, the second example shows two gauges. Now, let us assume this member is put for a bending. Then the neutral axis is there in the middle. The above portion undergoes tensile, the bottom one undergoes compression. Now, the top gauge senses a tensile direction and the bottom one senses the compression. Now, the advantage of this configuration is I can measure the tension, nullifying the impact of comparison on this. The next configuration talks about one in the linear direction and one in the transverse direction to understand how is the change in tensile and compression. The next configuration helps us to put two gauges, one on top, one on bottom in tensile direction, and 2 and 4, they are in crosswise direction at top and bottom. When you have more number of sensing elements, the advantage of using two sensors in the same direction is actually I am multiplying the output from my gauge system. Now, what I have done is I have put two gauges, one on the top, one on the bottom. For example, when the tension one goes, which is on the top, it goes on increasing strain. The bottom one goes in the opposite direction. Now, when I put these two gauges across a Wheatstone bridge, they give a combination of amplification. The similar thing happens when I do that in the gauge number 2 and 4. The compression or the crosswise transverse direction, whichever is sensed by gauge number 2 and whichever is sensed by the 4 is in opposite, and again hence they amplify. The advantage of using more elements in the same direction with the opposite direction nullifying actually helps to nullify the impact of transverse sensitivity of the gauges and also helps in amplification of the signal. So these are almost the same thing, but they have represented in a cantilever beam. Here in this, the top one goes on tensile. In the second image, the first one goes on tensile, the second one goes on compression, and that is what I explained. Now, there is another thing. Now we have seen how the tensile bending and tensile elongation is seen. The another part which normally we encounter is torque. The torque is actually sensed in shear direction, which means it is not linear or it is not aligning with the longitudinal axis of the member. It actually aligns with 45 degree because it's a shear state. We measure it in this direction. The first configuration shows how I can measure with the help of two. If there is any bending to be sensed because of torsion, I use combination 1, which is highlighted as 1 and 2 here. In the next one, when I need to increase the sensitivity on the same area, I do an amplification by providing both the members in the same configuration. In the third one here, I'm really interested in measuring the torque. So what I have done is, I have, like what I did for tensile force measurement in the previous one with one lateral and one linear. Here I have put 4 gauges, 2 for sensing in tension and 2 for sensing in compression. And that by actually what I do is I amplify the signal, I nullify all the transverse effect, and I only capture pure torque in this case. So this is a conditioner. This is a standard conditioner. I have not given the latest or detailed conditioner. This is the basic principle of using a signal conditioner. The purpose of this signal conditioner or the Wheatstone bridge conditioner is like here. Now here R1 is my sensing gauge, which is on the frame or any other member I have said. Now let us assume we will take we have used only one sensing element for the discussion purpose. There are cases where you can have more number of elements. For example, this R1 itself can be a combination of 4-5 gauges put in the same direction for the purpose of amplification. R1 will be a combination of R x plus x plus x, and R2 can be so. The purpose is to amplify. But here, for the discussion purpose, we will consider only R1. One resistance is there, which is going to be the sensing member on the vehicle component. It could be frame or any other thing. The remaining R2, R3, and R4, they form the part of the Wheatstone bridge. And we all know when there is output available, because of the change in resistance of R1, it is sent to the amplifier here. It is sent to the amplifier, and further the high level output voltage is given to the source. One simple technique used in this is like I can provide a shunt calibration. This is to check the linearity of the gauge. Now, I have a requirement of using the strain gauge for several months. For example, people who are constructing bigger structures and they want to monitor the function of the stress and strain levels, how they are changing based on the deterioration of the structure members, they may do it in a longer period. When I need to do this in a longer period, I need to check that whether the instrument setting, whatever I have done, is as per my initial measurement. If there is going to be a gain change or any other in this configuration, whatever I have done, then I may take a wrong value, and I can also miss out the real required information. So this shunt calibration is a method by which I calculate a shunt resistor with all the gauges R1, R2, R3, and R4 all balanced to each other, and there is no output at all. Now all the resistance are same. From the Wheatstone bit, there is no output at all, and hence my amplifier also doesn't give any output. Now this is called as zeroing of the bit. In the zeroed condition, if I am putting a high precision resistor or shunt across one of my resistors, then the output is going to change. What I do as a testing professional is whatever output of voltage that I see, when I'm connecting this R shunt, I will keep it as a reference value. And as and when I'm repeating the instrument measurement, I will cross check with the help of a R shunt resistor and see that my settings are same, so my readings are valid and they are exactly correlating with whatever I have done earlier. The next page shows how the shunt calibration values are calculated. The shunt resistor should be a precision resistor and it should be calculated with a given formula. And you can also do a calculation of what will be the equivalent strain if I'm putting a shunt of X value. You can also calculate. Normally, what people will do is they will be calculating the shunt resistor equivalent for 1000 microstrain, 2000, 3000, and so on. Generally, above 3000 microstrain, you won't have to do because the normal yield of the given best performing alloy materials are around that range only. So with this, we have just seen how the strain measurements are done, how customization of the strain gauges are possible, and with the help of conditioners, how I can amplify or how I can cross check is all that done. Now, this data, whatever you have seen, I have quoted one example from strain measurement, but the same is applicable when I do the measurement on vibration. Accelerometer is a sensor which is used for vibration. The vibration data is also similar to that of a strain. In strain, you have a varying strain values. In vibration, we have varying magnitude of the amplifier. Varying magnitude of my vibration levels at different frequencies or at one single set frequency. Similarly, the microphone. The microphone, instead of providing vibration or strain, they provide us the sound pressure levels with reference to amplitude and frequency. I can keep saying about sensors. Basically, I just took one sensor to explain how the sensing can be done for each type of sensor. For example, accelerometer, there are again the same things like the direction sensitivity, amplitude correction, amplitude magnification as and when required, and so on. So with one example, we can move on to the part of how the analysis actually happens after we digitize the data. So most of the transducers measure the quantities which are analog, and these analog output signals need to be moved to the computer for further analysis. Normally, the analysis is done in two modes. The first mode is time domain mode. Time domain mode is for simple viewing of a signal. How good is my signal? Am I okay? When I say time domain, the each and every milli event of the particular strain member. For example, strain. Let us say on every fraction of second, whether the amplitude is increasing or decreasing is all what we see in time domain. The frequency domain is the one in which all these increase and decrease of the amplitudes with a given inputs, how are they changing the frequency? Is the frequency remaining same or is it a varying frequency is what looked at. We will keep discussing further. We will also come to resolution, Nyquist and aliasing of the signals and the definition errors, peak definition errors, whatever we will be encountering. So here is an example of a time domain signal. Here, in this case, there is a delta t shown. The delta t actually shows that the time interval of each such a sample happens exactly at the same interval. This is called as a discrete time signal. But in real world, we may not have. One example of the this discrete time axis or time signal you can take is our sinusoidal, sorry, our AC sinusoidal signal itself can be taken as a discrete signal because it is a 50 hertz signal for a given ampere. The amplitude remains same and it passes one positive cycle and one negative cycle and so on. So in that case, it is a single frequency. Here, the delta t is same. But it is not the case when in actual field. For example, let us assume I am trying to measure the vibration or maybe the strain itself on a vehicle frame member when I am operating on a cobblestone road or nothing but almost equal to the rough road. Where there are different cobblestones and you get different sorts of inputs from the road wheels. The road wheels transfer them into the spring and the spring transfer it to the frame member which is bearing the load. Now, in this case, this delta T will not be the same. Okay, so when we do the analysis of time signal, we do it in a wide range of frequency, and we also need to look at whether the frequency content is within the given limit or not. Normally, the strain analysis and other things are run in time domain. When you need to look at vibration, noise, and other things, we look at in the frequency domain. The advantage of converting a time domain signal into the frequency domain signal is it will help easy visualization, which we will be coming into the next. Now, the same time signal, I have given an example of one single sensor. Let us assume, sorry, let us assume there are 4 or 5 channels for an example. In actual case, on a vehicle, when a new model is built, we measure close to 100 plus locations. The strain alone will be around some 50 plus locations, and you will measure around some 30 or 40 channels of vibration at different locations. For example, on the axle, what is the real ground note? On the frame after the axle, which gives the delta between what is there on the unsprung mass of the vehicle and what is there on the sprung mass of the vehicle. Now that tells us the characteristics of the swing. Now we will get into this. I have a set of channels and I have captured the data. One important thing what we need to look at is each sensor will have its own sensitivity. For example, I am collecting a time domain data. I am collecting a time domain data with one single strain sensor. It will have one sensitivity and its response is at some X rate. It will start giving a signal. Let us assume it is this. Now, there is another sensor. It could be a vibration sensor. It could be a mic or anything that will actually have a different sensitivity. Its response rate is different, and so it may happen at a different time with a small time lag or lead depending upon the time sensor. These difference between two channels or the difference between two such sensors is called as phase shift. Sorry. Now, as engineers, our main aim is to nullify this phase shift whenever we are dealing with vibration signals. So there are softwares and algorithms available for that. We have to make use of that. We also have to sync the channels, all the channels to one particular single time domain, and then carry out the data acquisition. And after that, it is all synchronized and it can be verified with different algorithms available as a part of your analysis software. So this is what I'm just representing how a time domain signal is converted into. I earlier referred to an AC signal. This is one single discrete frequency signal. It has an amplitude of positive and negative, and it's an analog repeating AC signal. The frequency is one single line. And when we are converting this, normally we use an algorithm called Fourier transformation. The FFT, which is shortly called a fast Fourier transformation, is one. Here I am representing this is what happens when you convert an time domain signal into frequency. The first one shows one single frequency, that's a discrete frequency, and the second one is a varying time intervals, and hence you will have multiple frequencies. The idea of converting from time domain to frequency domain, it gives you the advantage of looking at what are all the frequencies available. Are these frequencies within your designed limit or not? Are they going to cause a problem or not is what is interesting. Again, the same thing, the frequency domain. What we are seeing is a displacement on a cobblestone. Cobblestones are nothing but rough roads. We can take it as a reference. And here, instead of showing in one single lines, here they have put it as an envelope. For example, here everywhere there are going to be lines, and these lines are again captured with the help of a top one, called as an enveloping function. Normally, it is helpful when you want to look at the frequencies and do the analysis further. So Nyquist frequency is one important criteria. The Nyquist frequency is, let us go with this discussion that whenever I have to measure a data, I need to ensure certain Nyquist frequency. The Nyquist frequency is nothing but it is about capturing the data to the required number of samples. For example, I am going to deal with a signal of 40 hertz. Or to put it the other way, let us assume I am going to map an engine RPM of a vehicle. My engine has a maximum speed of 2400. When I say 2400 RPM revolutions per minute and I convert it into my revolutions per second, what happens? It becomes 40. 2400 by 16 is 40. So 40 is my interested bandwidth. Now what I should do as a sampling engineer, when I'm connecting the sensor to the instrumentation for data acquisition, I should at least ensure 80 hertz of sample. By doing this, so what I am doing is I'm ensuring I am not missing out any of the amplitude which is intended to be captured. Now here is a visual example of this. For example, this is the frequency, and here there is some X. Let us assume this is the 40 hertz signal, which I am really interested. Now I have sampled it at a 2 slow rate. Each dot here represents the sample that I am capturing. For example, here 2, here 2, here 2, and so on. What actually happens is, instead of capturing the real amplitudes which are supposed to be captured for the purpose of data acquisition, they only provide us limited number of data on each one by missing the amplitudes here. And actually, this signal starts looking like this. This error is called as aliasing error. This will not happen when I am using a sample rate of at least twice of the highest frequency of the signal. So let us assume for a signal of 40, I need to do it at 80. This number 2 depends upon the type of analysis you are interested. Most thumb rule, what we follow is 2.5 to be on the safer side, because once you capture the signal at a higher sample rate, you can convert it into lower sample rate with the help of the software. So what normally people who are interested in the frequency part of that will be looking at, not to miss a particular frequency, they will do it at 2.5 times of this sampling rate. For example, my interest is 40, at least I do it at 100. Okay, if I am really interested in frequency as well as the amplitude of the signal, and I want a very precise magnitude of the signal, then I need to at least look at a sampling frequency of 10. The same is again represented here. It is once again saying that how the data is being mixed and how we are going to get a different signal in place of the original signal. So to avoid the anti-aliasing, we need to remove the content that are higher. One possibility is that when I sample too high, there is a possibility that I get other EMI noises into my system. The EMI noises also walk into the system, and they also come and get submerged in the form of a real signal, putting you for an unwanted analysis. You may assume which is really not there in the system as a part of the system, and it can affect also. That kind of a wrong call also we can take during the. But one advantage here is today's acquisition systems are including anti-aliasing filters. If we are clear of what is the frequency that I am interested, then I can choose the right anti-aliasing filters and I can move ahead confidently with the data acquisition and further analysis. Again, the same thing, I don't want to stretch upon further in the same thing. And this one slide we will look at when my Nyquist frequency, if I am maintaining at 12, how I am reducing the error. For a 12, the peak error, which means this value, the possibility of capturing this peak is lost by only 3.4%. When I do it at 6, and it is the error, and the error increases as I keep reducing the sampling rate. So this one slide is particularly intended to show how the sampling has to be chosen based on your requirement of either the magnitude or amplitude. Sorry, the frequency. Again, I told there are loggers which are equipped with different types of filters. Anti-aliasing filters are there. Today, digital filters, everything is welcome. I put only 4 simple filters to show the importance of filters in data acquisition. The choice of the filter plays with the end result of the analysis. When here I am confident of the signal that it is not going to limit, it is not going to cross a limit of X hertz. Let us take for the same discussion point 40 hertz. Then I can use a low pass filter slightly above this 40 hertz and ensure that only any signal below, for example, let us assume I am choosing a low pass filter of 50 hertz. Only the signals which are below 50 hertz is captured. The reason for why I am selecting a 50 in place of 40, I will tell it in the coming slides. And so is the high pass filter. When I am so confident, I don't want any low frequencies. All I am requiring is any frequency above 60 hertz. Then I can use a high pass filter. No, I am very clear. It is one single frequency. For example, I am going to do an analysis of a machine shaft, which is going to run at a single frequency for a given rated RPM. Now, I can say I will use a band pass filter and I will say, for example, 40 is my interested. Then I may allow the filter to pass between 30 and 50 and look at what is the signal. And here, the band stop is one signal or one filter which you need, or you are so clear that it is an electrical noise. For example, most of the data acquisition system get into the problem of 50 hertz noise. You can experience that in most of the labs. But for the vehicle level related measurements, when you do it on the lab or any other environment, the most predominant noise which is getting captured is because of some grounding issues or anything. The 50 hertz electrical noise comes, and again it comes in harmonics. It comes at 50, it comes at 100, then 150, depending upon the amplitude of the noise disturbance, it keeps happening. So when you're so clear, I don't want this particular frequency to be a part of my signal, I use a band stop. And these are again the same thing. I will move to the next slide. Here, why I said why we need to use a 50 hertz in place I am requiring a tone. There is always going to be some amount of leakage because of the constructional error of the filter or by the algorithm of the error itself. So to ensure that I don't miss anything of my interested frequency, I slightly keep the low pass filter on the high side. And one important thing that we need to note is once the low pass filtering is done, there is going to be a slight phase shift. Depending upon the value of the low pass filter you have selected, the phase shift will happen, which means the time domain signal will not be exactly the same which is there in the vehicle. There is going to be a small delta t. This delta t needs to be corrected. There are methods to correct, and we can correct it with the help of the algorithm of the software. So while introduction of filters is necessary for doing the measurement without unintentional noises getting into the signal which is going to be used for analysis, you also need to be very careful on choosing the filters, choosing the value of the filter, and so on. Okay, right now we have looked at the different types of sensors, how the sensors provide the physical quantity, how it is getting converted, how the converted signals are used for further analysis. As I told, if it is a strain, it is for fatigue, it is vibration, it is for modal, then you do the modal analysis, or you want to do a transfer path analysis. For example, I need to understand how much of road shocks is coming from my road wheels to my driver's seat. So now what are the components that are there? The road wheels, the vibration of the road wheel, the vibration of the member to which the road wheels are mounted, then to the suspension, from the suspension to the frame. It could be a chassis frame on a bus, or it could be the unicoque frame of the car body. Then from there, the floor of the vehicle. Could it be cab? Could it be the body of the car? Then from there, the seat, and from seat, mounting frame to the seat cushion material. So now this analysis is called as a transfer path analysis. Here what I am doing is I am looking at how each and every component is reducing my vibration levels to make the driver comfort. I can capture the different accelerations of each and every component. I can look at and find out which one is transferring the unwanted vibration onto the motor. And further I can do. For example, I am seeing a low hertz frequency. Normally, the low frequency are the ones which affect the driver comfort. For example, let us take a frequency range of 4 to 8 hertz. This affects the abdominal portion of a human being. Now, this is not a desired frequency on a car seat. Now, let us assume for some reason, could be a component in my vehicle. It could be the structure, it could be the suspension or anything, which is actually taking the input, oscillating at that particular frequency, somewhere between 4 to 8 hertz, and it transfer it to the driver's seat. Then what happens is, then unintended vibration comes in and it provides a discomfort. Now, I need to eliminate this transfer path analysis is one setup which tells me which one is the root cause for this vibration and what parameter I need to change in that so as to facilitate cutting down that particular frequency. Now, this is one example we have seen. Now, all these measurements relies upon the calibration. When I say calibration, it is nothing but the sensor is supposed to produce some change depending upon the parameter. If it is temperature, because the thermocouple junction gives the difference between the two different junctions, and it gives in the form of a millivolt. It gives in the form of a millivolt. That millivolt is converted by an amplifier and it gives you the reading based on the calibration that is given. Now, similarly, strain. We also saw that the strain measurement can be used. The strain gauges can be used for measuring the force, torque, and so on. What normally people do is they will put the gauges in the required form. They connect them to the required way with the required number of amplification and all that. Then they connect it to that. With the help of a known source, they find out what is the output voltage. Very simple. I give an excitation, I give a known value. For example, if it is a torque, I give a torque of 15 Newton meter. For the 15 Newton meter, the given strain gauge bridge, how it is giving the output. Let us say X voltage. This X voltage is equivalent to 15 Newton meter with an error. So, similarly for force. So, similarly for strain. For strain, either you can measure by giving a actuator force or either by giving an actuator force or by the shunt calibration measurement, whichever we have seen earlier. One part is a theoretical calibration, the other part is physical calibration. Normally, testing professional in labs, they go for physical calibration because there you are certain of what you're doing. Why I am saying is the sections when you are so clear, when you are not confident of the calculation of your strain value or anything, the physical calibration actually helps. So this is just to show the importance of calibration. Calibration normally is done. Here I would like to say one important point. You may see some X value from a sensor. For example, there is a strain. The strain is taken to the conditional amplifier. Conditional amplifier amplifies and give bit, and this is an analog one. The analog is converted into the digital. The digital is again fed into the system. Now, there is going to be an error in my sensor. There is going to be an error in my conditional amplifier. There is going to be an error in my analog to digital converter. And there is going to be a small software error in my computer where I do that. This chain of errors what we have all put together form the measurement chain error. And as testing professionals, we are supposed to know whether I am within the given limit or not. If the given limit is not actually within our interested zone, then we may have to change the sensor or the amplifier or the software with which you can do the analysis. So that is the importance of calibration, and also periodically for sensors which are to be maintained over a long period of time, sensors deteriorate. The sensors deteriorate, conditional amplifier electronics deteriorate, and so on. So you need to periodically check them whether they are behaving in the intended form or not. Every labs will have this calibration procedures in place so as to ensure the accuracy of the measurement, or to put it in another way, how much uncertain you are. Generally, the preference and uncertainty given is more than 95% of confidence level is what with which we calculate or calibrate the gauges. Here I have just shown some representations indicating the difference between precision and accuracy. I may be not being correct, reading the correct value, but still I can be precision on given. All we require is both precision as well as accuracy. That is the importance of calibration. This is just a sample of a calibration report. Here it is like that. You have the sensor, you compare the output of the sensor with the help of a master one, and you see whether it is within the limits or not. I will not go into the detail much. So we all need to have a point that sensors may be good, conditioners may be good, softwares may be good, but still I need to periodically calibrate on a regular basis to see whether they are. And when I'm doing a customized sensing, when I'm doing a customized transducer on my own, and I need to calibrate it with the help of a master. So this is in brief about what as testing professionals we handle in sensing, instrumentation, and data acquisition. And for the part of putting a slight idea on what type of different analysis we do, I'll take few minutes and say, now let us assume I have put strain gauge on a particular location, and I have measured the acceleration, and I have measured force in some place. I have measured it. When it comes to strain, when I have a member and I am getting a result from my finite element analysis that there is a possibility that this particular area may crack after so many fatigue cycles. Now, what I do is I check, there is something called as percentage of certainty of survival, which means the prediction, theoretical prediction that I do can be 50% this way, can be 50% that way. That is the algorithm by which it is. Now, to check that, which means I'm saying, I'm getting a result of 50,000 cycles of given operation. Then there is a possibility it can fail, or it can initiate fail from 25,000, or it can even leave up to 75,000. To ascertain whether this assumptions and this calculations or this analysis, whatever I have done, what normally people do is they will do an strain measurement and do a real fatigue life calculation and find out is it complying. If it is complying and it is again within my given limit, here I have, for the discussion purpose, I have set a target of 50,000. Normally in strain life prediction, what people do is 2 into 10 to the power of 8 such repeating cycles. When it comes to vibration, people will look at the interested frequencies, whether the frequencies are detrimental for the structure, whether the frequencies are going to be disturbing for the commuting crew, or whether the different frequencies, vibrations, whether they are going to cause any noise into the system. Maybe the vibrations are within the limit, but do they cause a noise disturbance? Because as structures rattle, there is a possibility they can also bring in squeaking noise and so on. So it's a very detailed thing. We will not go much into the data acquisition part and further analysis part because it's going to take a lot of time. Now here I will just give an overview of what are the different types of sensors are used in current day automotives and what actually they are helping out in operating an automotive. In the last session, we saw sensors, instrumentation, or we can say conditional amplifiers or charge amplifiers or so on, and then to the data acquisition system. But here in vehicles, unlike the comfort of collecting the data, viewing it, taking it to the lab, checking it, checking whether they are statistically the signal is okay or not, whether I need to do some low pass filtering or high pass filtering, whatever is required, and then I do the processing. There, that advantage of time is available. I need not do it at real time on it. But in vehicles, actually, you need to do everything then and there. The sensors and actuators put together to the functioning in automobile. The sensors, as we have always known, they convert the physical quantity into the digital now. The actuator is a one which takes the input from the sensor and it gives the necessary, it takes the input from the sensor, does the necessary calculation or analysis, gives a decision to the next actuator whether to increase or decrease or anything else, whichever is intended. For example, I'll take one example, which I quoted in the beginning also. Let us take, there is a sensor in my engine to sense and tell what is my engine RPM. This engine RPM is one engine revolutions per minute, is one important data with which my accelerator pedal functions. The accelerator pedal itself is a sensor come actuator. The accelerator pedal is nothing but it is a potentiometer, an electrical simple potentiometer. So it moves in an angle, right? As we press the accelerator pedal, it moves in an angle. What happens here is my resistance initially at some zero. So I get some X voltage as the output from this sensor. This is one thing. Now, when I'm pressing the pedal fully, it goes to 100% of the time, which means the resistance is at some X value and equivalent to that it gives. Now, this accelerator pedal from 0 position to 100 position will have different varying resistance values, and hence the output will change from X to Y. Now, the engine RPM sensor, this accelerator pedal sensor, both are connected to my engine control unit on a vehicle. The engine control unit now takes the sensing from both the engine RPM and my throttle speed sensor. Now, it also takes other inputs like what is the demand? What is the demand on the given road? How much of torque is produced? How much of torque is produced is again sensed from the help of a, again, it is taken from the help of a calculated value of engine torque based on the fueling quantity. How is the fueling quantity is known? It measures the fuel it is going into the engine with the help of a metering unit. It is taking the input from a metering unit which monitors how much of flow is there. My intended flow is X value. The current metering value says that it is X minus delta for the given accelerator pedal position, which is the demand given by the driver for the given value of engine revolutions. Let us say he is demanding more, my engine RPM is less. My engine RPM is less because the demand on the engine, the demand torque on the engine is high. So what I need to do now is, based on the throttle position, I have to give an input to the metering unit to open up further, allow more flow. Once the fuel flow happens more, that again it gets connected to the throttle valve, which is onto the engine, which also increases the amount of air that has to be sent into the engine, because the fuel has to go and air has to go. Once both goes into the required volumetric this one, then my firing happens, the torque developed by the engine move, and then the vehicle accelerates further. So this much amount of processing happens with the help of sensors. And it is there in each and every part today. Earlier, we used to have a simple accelerator pedal. You will have one lever. That lever will control the fuel injection pump lever. It will either open, close based on that. It is again a simple mechanical system. But today, it is not. It is done in a more precision way, in a more efficient way, so as to control the amount of fuel. Because in the older methods, what you do is, it does by an approximation. For a pedal travel with the linkages, there is a backlash or anything as days goes, there is going to be small change. Even for the small change, it may inject a slightly higher. But today it is not like it actually on time calculates whether the developed torque is based on to the requirement or not, based on the position of the pedal, based on the position of the engine RPM, amount of the fuel flowing, amount of pressure maintained for the injector to inject the system inject the fuel into the cylinder system. Do we have everything in place? Now, is it okay? Can I trigger the further increasing of fuel to the engine? Should I need to increase or decrease based? The reverse happens when I'm trying to take the pedal. Take the leg out of my pedal, and the operation actually slows down. It says, "Come on, engine speed has to slightly reduce," as the driver is intending to decelerate the vehicle. Maybe he is going to halt or something. So every instant, this monitoring and controlling keeps happening on a vehicle. So here are some examples that I have put, like what are all the sensors and where all the sensors are used. I would say currently about 100 plus sensors are there on a vehicle for sensing, controlling, and operating the vehicle in the most efficient intended manner. So the cab saloon temperatures, they take care of the comfort and ventilation, because this sensing gives the temperature. For example, let us set 23 degrees Celsius or so. This continuously monitors and say whether the AC compressor needs to run further or it can slow down so as to increase or decrease the cooling. And ventilation, whether the ventilation is good or not. There are systems which also look at how much amount of oxygen is available. For example, we normally put the AC in the cab mode. Most of the operation, what we see across people is they put in the internal cab circulation because they don't want the fuel to be wasted. But will it be okay or not? There are certain automatic AC HVAC systems. They control the ventilation also based on the oxygen levels inside your cabin. Either they can open out for external mode of airflow or internal air circulation. So engine sensors, they are used for the purpose as I said. The exhaust system, it is mainly going to cater for the use of whether the exhaust gas going out is meeting the given regulatory norms, whether the nitrogen oxide levels are okay, whether the carbon monoxide content in my exhaust is okay or not. Based on those sensings, it again gives a feedback to the engine control unit to say the mode of operation for optimizing further whether required to give extra pressure or not. The tire pressure monitoring system, this is one which we all commonly see in our cars. It gives an indication of whether the pressure is okay given a set value or not. If there is a lesser thing, it keeps indicating us. The body control unit is one unit which controls the operation of the engine, along with the vehicle speed and transmission related signals. It says whether the vehicle is operating in the given boundary conditions of the particular. For example, it needs to tell whether the vehicle is on track. The route map is fed into the intelligent transport system. It says whether it has crossed the given boundary. It helps in fleet management as well as passenger warning system. Okay, then telematics is one unit which helps for the fleet management. It gives the data for people whether the vehicle is operating within the given conditions of, for example, harsh braking by the driver. Fleet managers, they can, by sitting in the office itself, they can monitor whether the driver is deviating from the given route, whether the driver is doing a harsh driving, whether there is a traffic anticipated in the route which we are going to go further, any route diversion possible, and so on. So these are the sensors that are used. Mostly the sensors, whatever we have seen, depends into the category of sensing, force, torque, position, flow, pressure, and so on. In case of automotives, some sensors are coupled with actuators and some sensors individually give a input to the concerned control unit so as to take the necessary decisions. Normally, this is the schematic layout which we use it as a ready reference for what kind of change and how the sensing is done. What is the principle of a parameter change? For example, it is change in induction. You have a magnetic engine RPM sensor or cam position sensor. You have a magnetic sensor which cuts the inductive this one when something is rotating, and it is given as an analog signal to the signal conditioner electronics, and further it gives it into the form of a engine RPM to ECU. ECU is engine control unit. TCU is transmission control unit. This engine control unit and TCU needs to interact. So the body control unit, again based on the ECU and TCU functioning, the body control units provides the input to the passenger and as well as to the fleet management system. ACU is after treatment control unit which controls the emission and other things, and ABS ECU is the one which takes care of the braking part. So all the interaction of I've just categorized into very simple 3-4 types, but to put it in a right way, an engine control unit of a given automotive, let us take Ashok Leyland truck, it deals on the moment with 118 plus such sensors. So that much amount of information flow is there into the engine control unit. I'm skipping these slides, please excuse me, because it's again going to tell the different sensors and the purpose of that. I think I have briefly explained the purpose of them. Yeah. So in the engine control unit, whatever I was talking, it used to take inputs from 118 plus sensor on a moment at a sampling frequency of 133 hertz. So you can look at the amount of data that is processed instantaneously to give decisions to the vehicle operation. So the operation is controlled by this given architecture. There is an engine ECU. There is a CAN area network which happens, which is there. There is an after treatment ECU. There is an ABS ECU. Here ABS ECU is anti-lock braking system. The main purpose of this ABS is to take inputs from engine, compare it with the road speed of the vehicle, and to either decrease or increase the deceleration rate. For example, let us assume this portion of the vehicle is on a non-wet surface, which we normally encounter. Is like the right side of the vehicle is on a dry road. On the left side, it's a slippery wet road. Now, based on the running of the vehicle, assume it is an unladen vehicle. Because of the lesser mass, there is a possibility that these wheels can spin at a faster rate than this. The ABS control unit is a one thing which actually monitors the RPM of each and every one, and when there is a difference, it tries to equate the RPM of both. So when let us assume this starts slipping, then he slightly decelerates this wheel by applying a brake and bringing it close to the RPM of the LH, so that vehicle drifting or anything doesn't happen when somebody is applying a brake. So the body control unit I already explained. Telematics, we saw what it is. AMT or AT, the TCU, it is nothing but they have put it with a different name. AMT is automated manual transmission, and AT is an automatic transmission. The first one is a purely mechanical. With the help of pneumatic actuators, you change the gears. In automatic, it is purely hydraulics. The hydraulics and the engine, the transmission control unit takes care of the changing of it. Just a simple portion of ECU, as I told, about 118 channels are currently dealt by the ECUs. You can keep adding the number of channels that inputs that you want also to the. This is one schematic layout where there is, I have taken one 18 pin connector. Yeah, it's an 18 pin connector onto which how many such sensors are there? This portion is from injectors. This portion is from injector, and this is from lambda sensor. When I say lambda sensor, it is a sensor which gives the value of oxygen available on my exhaust, and so on. There are other sensors too, and they are all coupled to this ECU. This keeps interacting. They provide the data, this keeps interacting, and they control the engine, as I explained in a very brief way. So this is again an architecture of how the information flow between different ECUs and the control modules happen. AMD, the same, that one was for engine, and this is. So for making all these functioning properly, whatever we saw, no, the engine control unit, the CAN architecture, the CAN architecture to work, what testing professionals or the engineering professionals do is they do a base vehicle calibration, and the base vehicle calibration is done so as to give the required amount of fueling and power to the engine so as to meet the demands. Once that is done, then they will do a drivability assessment, whether the vehicle is good enough to climb on a given grade or not, whether the vehicle is able to climb the given grade or not, whether the vehicle can operate on a plane with a given higher gear possible. Because the moment I go for higher gear, the fueling comes down and hence the fuel efficiency. So drivability assessment, I just spoke two parameters. There is a lot more to that. We will not get into the depth of that. So this drivability assessment is done. Then engine protection. Now let us assume we are coming down a heavy hill, down gradient. There is a possibility if an unknown driver is wrongly choosing a gear and the engine RPM is going to exceed a certain limit, there is going to be a critical speed for every engine, right? A given engine with a given purpose of design cannot exceed a certain limit. Now, this engine protection is very much necessary. If that is what the engine RPM says. It gives the instantaneous revolutions per minute of the engine to the ECU, and the moment when the threshold of the given engine RPM is crossed, the engine protection is enabled. The special feature calibration, like we have seen some cruise control, we in cars and other things, economy mode, power mode, and so on. So when somebody is a bit racing type of a guy, he wants to better performance, he is not bothered, you can operate the vehicle in power mode so as to facilitate the best possible acceleration given to the sorry. So these are the special features. DSM is nothing but diagnostic systems management. We will see that in the coming slide. And OBD2 is onboard diagnostic tool. This OBD is a regulatory requirement as well as the diagnosis system management. These both are regulatory. DSM helps the manufacturer or the service station to find out what is the issue, and OBD is to for the government to check whether the vehicles are operating within the stipulated statutory norms of the country. The protocol and altitude trends. For example, I can give some fueling and other things based on the given driving assessment in my current operating altitudes. For example, places like Chennai, Bangalore, Mumbai, and all, they are at some. Now, the same vehicle, when I take it for an higher altitude, let us say I'm taking it for Kashmir or somewhere in northeastern states where the altitudes are 2000 plus, the amount of oxygen available there will not be sufficient. So, for the given lesser amount of oxygen, how should be my combustion happen? That is what is called as an altitude trial. This calibration happens physically on the site with the vehicle running there. We calibrate it. We have a lab to simulate a base level performance at our engine testing lab. Once that is done, with the base level performance lab, we will take it to the required spot and do the final calibration there. Again, the same, I will not get into this. So this is just an overview. For example, engine protection, one example I gave is the engine overrun when I'm coming down a gradient. There is also a possibility my my driver or operator has forgot to fill up coolant. There was some loss, there was some service activity. They have not topped up the coolant to the required. There is a sensor which measures the coolant temperature, and it says that engine operating temperature, the coolant operating temperature has exceeded a given limit. When the exceeded limit is known, they will look at the reason for why this is. Is it because of my? Please don't look at this fan. This is just for fun. Somebody has put a table fan. Actually, the fans on the vehicles will be different from this one. It will be a electronically operated fan, or sometimes we will be using a electro viscous fan, which means the trigger is by electronics and the functioning is by the hydraulic fluid coupling principle. So when the temperature is exceeding, an input is given to see whether the fan is running at a given RPM. There is something called as a lookup table inside my data set. The engine control unit will have a clear data of, for a given temperature, should my fan RPM be X or Y? My coolant pump should be operating at this particular RPM. These inputs are taken, they have seen on a momentary basis, and when they see if it is not due to, if it is due to the fan running at a slower speed, then a trigger is given to raise the fan RPM to the required limit. This is one example there. And for example, there are certain other parameters. Even after the switching the fan also, it is not able to bring down the coolant temperature. Then what happens is the engine unit takes a protective measure. It controls the torque value. We have scales of giving the torque based on the temperature. For example, my allowed temperature is say 100. And when I am at 102 degrees Celsius, I would say reduce the torque production by the engine by some X percentage. When it is at 105, reduce it by some more X percentage. And let us assume it has touched to the value. There is something big in the engine. There is something wrong has gone into the cooling system of the vehicle. I cannot do anything further. Then in that case, we give a command and halt the engine and say the cluster gives a message. The cluster in front of the driver gives a message with the red flash, says that engine error, there is a problem in the engine. Keep the vehicle idle, take it to the service station nearby by towing or something. So this is how the engine ECU interacts with the different types of sensors, how the calibration is done, and for the diagnostic purpose, I just represented one thing. Lot of such message interactions happen between. Lot of such message interactions happens between different ECUs and so on. The control is done in this way. Telematics we discussed. This is just a slide to show what are all the parameters: the vehicle speed, trip distance, harsh braking. Are the drivers really using seat belts? There is a sensor to tell us whether the seat belt is on or off. How much is the fuel consumed? Is there a diesel pilferage by the driver? For example, you can see some drivers, they reach the required location, they try to drain the fuel from you. When there is an instantaneous level change, an alert is given to the fleet manager or to the owner. The battery voltage, whether the battery is healthy or not. Will the battery be able to crank the engine? For example, I park it overnight in a cold winter. I park it overnight and then come and recrank the engine in the morning. Will it be sufficient enough or not? Such data are gathered and information are fed through a server to the fleet owners or to the fleet owners or the management team, and give an input and see how the operations can be done in an effective and efficient. So finally, this is about ADAS. We all might be seeing that ADAS is one new feature which is catching up in Indian vehicles also. The automotive or the Indian country itself has a long way to go in this. These sensors here give about certain volume. ADAS is Advanced Driver Assistance System. When I say BSIS, it means Blind Spot Information System. For example, I am trying to approach on a turning. Let us assume there is a culvert or something. When my vehicle is going near, it gives an information or it gives an alert to the visual alert to the driver. When I say move, MOIS, it is a moving object information system. This sensor tracks the instantaneous movement against coming against the vehicle. For example, somebody from the side road is coming or who is in the service lane suddenly comes into the path of your vehicle, this system gives an alarm to the driver saying that somebody is walking into your track. Don't go further, please stop. AEBS, this is one advanced stage of the ABS systems, whatever it is. AE is electronically controlled braking system. Here, not only the wheel spinning and the difference of rotations between the possibility of wheel lock and vehicle drifting, here people also look at the yaw rate. For example, whether there is a sudden lane change, it is going to have some lateral acceleration. These lateral accelerations are sensed, they're calculated whether at these speeds, whatever lateral acceleration is happening, will it cause a tilting or not? If it is going to cause a tilting, I have to automatically pitch in and I have to control the speed. So this is the AEBS system. And DD is driver drowsiness alert and warning. So on a long run, when somebody keeps on driving for a few hours, like 7 hours, 8 hours, for the reason of making the trip on time, and there is a possibility that the driver can start feeling sleepy. The eyes are tracked, eyeballs movement are tracked, and if it is showing that the person is going to sleep in few seconds, a warning system is given either in the haptic form in the driver. For example, the seat vibrates, or there is an audio signal is given to the driver for him to wake up. Now again, LDWS is a similar case, maybe due to driver sorry, maybe due to driver drowsiness, or maybe for the reason of changing the lane. When there is a lane departure warning system, I am not giving any input to the steering wheel. Something has gone wrong. My intention, or my, in the sense, the driver's intention is to travel on the straight path, but whereas the vehicle is slowly drifting from lane A to lane B. This is tracked by a sensor, and it gives a warning signal to the driver, say that please, you're actually going out of your lane. There is a possibility that either someone who is coming at a higher speed from the rear can come and dash against you. All these put together, this BAS, MOS, ABS, DDAW, and LDS, all put together, we call it as an ADAS. There are different levels of ADAS implementation, level 0 to level 4. And we are actually, as a country, we are in the stage of maturing. And in some cases, automatic interventions have already come in some passenger cars, though it has not yet come in the general implementation. What the country is now looking at is limiting it with the warning system rather than providing the control of changing things on its own without the driver's control. So with this, I will finish up my presentation.
Thank you, sir.
I hope it was useful.
Yes, it's quite interesting and quite useful, sir.
The problem is the subject is a very detailed subject. If I take sensors for strain gauge alone, we can talk for nearly 1.5 to 2 days.
Yes,
My
yes, sir.
training program, when we attended for strain measurement and analysis, it itself went for 2 full days. That was
Yes,
so the subject is very vast. I try to touch upon wherever it made sense for me.
Yes, sir.
Is excuse.
It was informative, sir. The information, what you have presented.
I just thought that as an eye opener. Yeah.
Yes, sir. That it was an eye opening, sir. Sir, actually, the 2 questions I have raised in
please.
One is that does AI reduce the need for physical sensors in some applications? One of the participants raised.
Yeah. Yes, it is right. Actually, it is right. Actually, the AI is facilitating by. I think I showed one sensor, ACU, after treatment control system. We actually get into that. For example, earlier, if you look at when the Bharat Stage 6 was introduced way back in 2020, sorry, 2021, we had some sensors there. But today, based on the modes of operations and based on the what normal inputs with the given rating of engine, driveline, and so on, people were able to eliminate few sensors because every company looks in the value engineering part. So certain sensors can be eliminated and they can give a model. This working model or a lookup table, what I would call, is an output or is an outcome of using AI. Like that, many such AI things are done. Yes, it is possible. It is possible, but one thing is we cannot completely eliminate critical sensors. But wherever it is possible, you can actually reduce the number of sensors. Yeah.
Thank you, sir. Thank you. So another one question is okay, the challenges in acquiring accurate data from multiple sensors. Is there any possibility of acquiring data, accurate data? Is there any challenges, sir, in acquiring it?
It is quite possible. It is quite possible. And let us all accept that measurement itself is going to have some percentage of error, or I would put the other way, uncertainty. Okay. So we
Yes,
need to know how close I'm required. That is why I said about the measurement chain error. So you need to select the sensor. For example, I can use a thermocouple to measure temperature. A thermocouple has an error of plus minus 2 degrees Celsius by the specification. And when I say a thermocouple has an error of plus minus 2 degrees Celsius, I refer to a K-type thermocouple. Of course, we all know there are different types of thermocouples. This is one input. Now, there is a possibility I need an accurate value. I can take an RTD sensor. RTD sensor is more precise. Right. The difference between this is RTD is a slower one. The thermocouple is a faster one. So based on your need of measurement, you can minimize the error as good as possible. And second thing I would like to add upon is that is where the calibration comes in place so as to ensure you are close to your intended target. Yeah, that's it.
thank you, sir. Is there any queries that can be get clarified with the resource person, dear participants? I would request our coordinator of the FDP, Dr. K.S. Pravan, sir, if you want to make any note of the session, sir.
Sir, thank you so much, sir, for your great presentation today.
Thank you.
I'm thankful to Ashok, Leyland, Chennai always. Sir, we have put up an laboratory which is worth over 65 lakhs at our institution. It's being well received by students and faculty fraternity of our institution, sir, and nearby too.
Sir, I have visited your lab. I have come to your campus once, somewhere 2 years back. I've seen that. It's a wonderful lab.
Yeah, sir. And we are thankful to both Sasikumar sir and Muthukumar sir for accepting our invitation to depute and great expert you to this session today. Thank you so much, sir.
Oh, welcome and thank you. Once again, thank you to all.
Thank you, sir.
Thank you, sir. Now, at this outset, I take this opportunity to thank our resource person, Mr.G.Mahendrakumaran, who is a Deputy General Manager, Ashok, Leyland, Chennai. So, really, our session was very insightful and very informative regarding the sensors. Definitely, we will incorporate in our studies and also in our future careers, sir. Thank you, sir. Thank you for your presentation, and thank you very much.
Thank you.
An announcement to the participants. Okay. Now, so far we had 2 sessions. The next session, third session, will be at 2:30 p.m. After lunch, you will be having the third session at 2:30 p.m. Dr. R. Rajendran, who is a professor from SRMIST, he will be taking the session on Python for engineering simulations. This is the topic. So he will be addressing on the topic at 2:30 p.m. So we're expected to join the session 10 minutes in advance to 2:20. Please do join, and we shall start the session sharp by 2:30 p.m. Thank you very much. Welcome back to our 6-day FDP, the post-lunch session. Gentlemen, as we announced earlier, Dr. Rajendran from SRMIST of Science and Technology has joined us. He will be presenting his ideas on Python for engineering simulation is the topic. Before we get into the topic, let me have the pleasure of introducing the resource person of today's session. Dr. Rajendran, he is a highly accomplished academician, a researcher having more than 30 years of experience in engineering education, research, and academic leadership. He is a professor in the Department of Automobile Engineering at SRMIST of Science and Technology, Chennai. And he is expertise in materials and surface engineering, machine learning, electric vehicles, autonomous vehicles technologies. Throughout his career, Dr. Rajendran has consistently bridged the gap between academia and industry through collaborative research, industry-sponsored projects, student development initiatives, and professional society engagement. Dr. Rajendran has received prestigious recognitions, including the SAE India Foundation Grow Award in the year 2022 and the SAE Excellence in Engineering Education EEE Award in 2019 for his outstanding contributions to engineering education and professional development. With strong expertise in research, innovation, industry collaboration, and student mentorship, Dr. Rajendran has made significant contributions to advancing engineering education and automotive technology in India. So, ladies and gentlemen, with this brief introduction about this post-lunch session resource person, Dr. Rajendran, and on behalf of Department of Mechanical Engineering, Knowledge Institute of Technology, we wholeheartedly welcome you, sir, for this session, for this 6 days FDP program. Over to you, sir.
Okay. Thank you, Dr. Karthikeyan, for the nice introduction. So, today we will be discussing or talking about the Python for engineering simulation. So it has been structured in such a way. So first we will be trying to understand what is the need for programming, why we want to do the simulation, and why particularly we are trying to use the Python. And then we will try to see what is the workflow in the Python simulation, what are the steps involved in it. And then we will try to see how we could visualize it, how we could try to use the Python and then try to do it. And then we will go into the some parts of simulation of mechanical systems. And we will just have a case study, which is a simple one, which we will be able to understand easily. That is the way I've just structured the lecture. So we will have something like 4 parts in it. And if time permits, at the end, we will try to have a small test, which will be for 15 or 20 minutes. It's an MCQ. So we will just try to see how you could, whatever the knowledge you have gained, that has been fulfilled or not, that we could just assess at the end. That is the idea. Now I will just try to share my screen. Hope my slides are visible.
Sir, it's very clear, sir. You can go ahead.
Okay. Yeah. I'll just switch off the video because that will have. So hope everything is clear and audible. I'll just.
Yes, sir. It is clear, sir.
Yeah. Okay. I think we have participants from various colleges. Is it from industry we have?
No, sir. All are academicians, sir.
All are academicians. And they are
Academicians
mostly
from around the
mechanical.
5 states of India.
Okay, that's fine. So I will just try to give some examples, mostly on the mechanical. I've just also touched upon something on the how the Python has been used in civil engineering, aerospace, automotive, and electrical. But whatever the example or the case study I've taken, it's a normal heat transfer, which everyone can easily understand. So that is the way I've just structured this lecture. So good afternoon, everyone. And as introduced, I am Dr. Rajendran. professor in SRM Institute of Science and Technology. So my domain has been already talked about. So I have tried to have my scholar who have done research in material science is done on the coating, for which we have done the corrosion prediction using machine learning. So now we need to have the skills, not only the traditional one, but also we are into the digital world. So we need to see how we need to equip ourselves, even though we are a faculty, we need to see how we need to equip ourselves in various skills, so that what are the skills we have that we could transfer to our students. So who are our main, what you call the customers, or the persons who will be finally will be taking care. So with this note, I'll just go into the topic. So we have the Python for engineering simulation. So we'll just look into the why the programming matters in engineering and how the Python for simulation, AI and data analytics works. So see now, let me ask a simple question. How many of you use a calculator for solving engineering problem? So when I ask this, I think almost everyone will be using the calculator. But now, if I just ask a question, what if instead of solving one calculation at a time, a computer could solve 10,000 engineering calculation in few seconds? So what if you could predict whether a component will fail, or test hundreds of design alternatives, suggest the best design automatically, and also continuously analyze the data from the sensors? So this is where the programming enters into the engineering. So basically, we know what is the traditionally the engineering is largely based on the calculations, experiments, and experience. So if an engineer wanted to test a new design, they would design, build, and test, and then try to make the modification in the design and then manufacture it. So this process will take weeks or even months. So I think this concept of the design, build, and test, all the student competitions, the SAE India and the southern section is doing. So this competitions has this concept of design, build, and test, which they are doing. So even this could be done or implemented with the students also. So today, the industries will not be able to afford such delay. The companies such as Tesla, Tata Motors, Boeing, Airbus, and ISRO cannot build hundreds of prototypes before finding the right design. So instead, what we try to do is first create the digital model and test them virtually. So when you talk about the modern engineering, it's driven by simulation, artificial intelligence, automation, and data analytics. So when you consider a vehicle is being manufactured, engineers try to simulate the crash performance, vehicle dynamics, battery behavior, and aerodynamics. So similarly, before an aircraft flies, the engineers simulate the airflow, structural vibration, and fatigue behavior. So this is the case with the civil engineer. When they are constructing a bridge, so they try to simulate the wind loading, traffic loading, and earthquake effects. So all of this happens inside the computer. So one of the most popular tools that enables the engineers to perform these activities efficiently is the Python. So Python is simple to learn, but it's very powerful enough for the advanced engineering applications. So engineers use the Python to create the mathematical model, perform simulations, analyze experimental data, visualize results, and build AI-based solution. So for example, when you design a disk brake, so engineers can create a mathematical model, simulate the heat transfer or the heat generation. They could easily predict the temperature distribution and optimize the design automatically. So this task can now be completed within minutes because we are going into the digital era. So what is the main thing which I would like to say is the modern engineers are not only expected to understand the engineering principle, but also they need to use the digital tools effectively. So for this, Python acts as a bridge between the engineering fundamentals and modern intelligent engineering system. Yeah. The next, talking about the engineering in the digital era. Suppose if you are working in an automotive company and you have to design a new suspension system. So instead of building 10 or 20 physical prototype and testing each one individually, so it's better to create a digital model, and then with that you can test something like thousands of design combinations using the computer. So usually everyone will go for the second option with the digital world. So when you talk about the traditional engineering and the modern engineering, the traditional engineering depends heavily on the manual calculations. Then you have got the physical prototype. So you have got the repeated testings, so which will be very time consuming. For example, if an engineer design a gear and it failed during testing, the engineer has to redesign it, manufacture it again, and repeat the testing process. So every time there is an iteration which requires additional time and money. So that is the traditional approach, which has got several limitations. So you got the product development will be very slow, and then the cost is very high, and then optimization is also difficult because the engineers could evaluate only a limited number of design alternatives. Whereas when you talk about the modern engineering, the entire engineering has changed. So this depends heavily on the digital modeling and simulation, artificial intelligence, and smart manufacturing. So engineers can evaluate thousands of possibilities before manufacturing can be started. So even if you are familiar with the Formula One racing teams, they don't build hundreds of wings and then test it physically. Instead, they use CFD simulations to study the airflow, drag, and downforce digitally before they select the best design for the manufacturing. So this is what we are just trying to talk about in this slide. So we are currently in the Industry 4.0 era. Technologies such as digital twins, smart factories, AI-based monitoring systems, real-time analytics, and autonomous systems generate large amount of data. So we require the programming to process, analyze, and use this data effectively. So the programming and simulation are the skills which are very essential competencies in the modern digital era. The next, talking about why we need to go in for the simulation. See, you could see some examples given here. So if you want to design as a civil engineer, when you want to design a bridge, when you would like to discover the design problem, whether it's before construction or after the construction, obviously you wanted to know the failure before construction. That is the purpose of simulation. So why we wanted to go in for the simulation? So simulation helps the engineers identify the failures early, reduce the cost, save time, and improve the performance. And thereby you try to minimize the need for physical prototypes. So that is what we could see the Tacoma Bridge vibration. So this is the bridge collapsed because of excessive vibration and resonance. At the same time, we did not have the simulation technology during that time. So today, the same problem is given. The engineers can simulate the wind effects, structural vibration, and the resonance condition before you start the construction of the bridge. Then you have got the vehicle suspension. So this is one of the application in automotive. So if the suspension design is poor, passengers will experience discomfort, excessive vibration, and poor handling. So engineers therefore simulate the suspension behavior before manufacturing. And one more example, we have got the aircraft wing, which experience vibration continuously during the flight. So if presence occurs, so then it means we have got the fatigue damage will increase and the structural failure may occur. So engineers perform vibration simulation before the flight testing. So this is the application in the aircraft. And similarly, when you take the machining operation, so you could see the CNC chatter vibration. So when you go in for the machining, you have the chatter vibration, which causes poor surface finish, reduced tool life, and higher noise level. So simulation will help the engineers identify the unstable machining conditions before production. So you could, from the examples, you could see how the simulation plays a major role. This allows the engineers to detect the problems before spending the money in building the product. So all these examples, whether it's a bridge or the vehicle or the aircraft or the machine tool, all demonstrate the same principle. The engineers use the simulation to predict behavior before the failure occurs, how it works. So basically the advantage of the simulation, it allows the engineers to learn from failure instead of building the prototype and then having a expensive real failure. So which this virtual failure results in the safer, smarter, and more efficient product. So next, talking about why the programming is important in engineering. Suppose if you want to solve the stress distribution in a component, if it is a 1 or 2, you could do it manually. But when you want to analyze thousands of design variation, so in such case, you could not handle or do the manual calculations efficiently. So modern engineering problem involve large scale calculation, automation, simulation, optimization, and data driven decision making. So the programming enables to perform this task quickly and accurately. So you could get the tasks which are very repetitive, you could just make it automated, and then you try to, this will help you to solve the complex problem, which will reduce the human errors also. And you could also try to see how you could speed up the product development. So you could have the simulation before the physical prototype building or the testing. So when you consider the modern vehicle, this has thousands of sensors and generate large amount of data every second. So analyzing it manually, all the information will not be possible. So the programming helps us to handle such complexity. That's what we have been talking about, this all complex mathematical problem. Similarly, this is not only applied in the mechanical, but it has been applied in the different engineering disciplines. And the programming allows to automate the repetitive task, evaluate multiple design alternative, and also develop innovative solution that would otherwise be difficult or impossible to achieve through manual methods. So basically, when you talk about the programming, so this allows the engineers or the programming transfer the engineering from the manual problem solving into intelligent problem solving. And we have talked about some of the engineering applications, which we'll be dealing in detail. So next, why Python for simulation? See, there are a lot of programming languages or softwares. Why especially we are just talking about the Python? Even though we have hundreds of programming language, why do engineers prefer this? Because there's got a unique combination of simplicity and power. So even the beginners can learn it very quickly. So it's simple and readable one. It's easy to learn for the engineers, and it is got an excellent visualizing tools. So it was also you can easily integrate with engineering softwares, any sort of softwares like ANSYS or MATLAB, SolidWorks, CATIA, and other CAD tools also. So this allows the engineer to automate the engineering workflow and connect different software environments without any difficulty. See, another major advantage is Python is open source and free for use. So even anyone can use it. The students or the researchers can use it because it does not require any software license. So with the strong community support and thousands of engineering libraries, Python enables the rapid and efficient solution development. So Python, it's used basically for its simplicity, power, flexibility, and industry relevance. So talking about the Python libraries for engineering, so imagine you are building a car from raw materials and every time you need some transportation. So which will not be very efficient. The same idea has been applied to the programming also. So instead of writing every function from scratch, Python provides libraries which are collections of ready-made function and tools which has been developed by the experts. So these libraries will significantly reduce the development time and allow engineers to focus on solving engineering problems rather than spending time creating basic computational tools. See, I've just listed some of the important library. NumPy is a numerical computation and matrix operation has been supported by this. And also you have the SkyPy, which is provides the advanced scientific and engineering functions for the optimization, integration, and signal processing. Then you have got the matplotlib, which helps the engineers create the professional graphs and visualization, which make it easier to understand and communicate the engineering results. And you got the pandas, which is widely used for handling and analyzing the large data sets which has been generated from the experiments, simulation, and other data. So Python also provides powerful libraries for AI and ML, including TensorFlow and PyTorch and scikit-learn. These tools enable the engineers to develop predictive models, intelligent monitoring systems, and automated decision-making application. So for example, if an engineer wants to calculate the stress values for 1 million data points, so writing a program from scratch would require extensive coding. Whereas when you use this NumPy, the same task can be completed within a few lines of code. So the Python libraries, it's basically, you can say it's a ready-made engineering tool that could reduce the development time and increase the productivity. So next we are just trying to compare the Python with other tools. So we have just compared the various features, how Python is. So we're just trying to see how it's very fast, the cost, there is no cost involved in it, and it's got a powerful capabilities. So it has got a good support. So the organization can develop solutions more quickly while reducing the software development cost. So and also the it's easily integrate with the industrial softwares also, so that you speed up and then improve the overall productivity. So that is the reason why the industries are shifting towards Python. So when you have a manufacturing company can automate the design calculations, generate engineering reports automatically, and run simulation workflows with minimal human intervention, such capabilities will improve the efficiency, thereby reducing the errors also. So Pythons help the industries to innovate faster, automate the workflow, and reduce the development cost. So that is the reason why the industries are shifting towards Python compared to the any other programming languages. Then next we will talk about the industry adoption of Python. So many people think Python is only used in the software companies, but in reality, Python has got most widely adopted technology across various engineering industries. So its versatility allows to be used in sectors ranging from automotive and aerospace to healthcare, energy, robotics, civil engineering, mechanical, and so on. Because it's got a fast development, AI integration, lower software cost, and easy scalability and large development support. When you just look into the various industries, so Python supports the simulation, and then you'll be able to optimize, and then you could also go in for the smart factory automation. Even when you talk about the healthcare application, so you use Python for medical imaging and diagnostic data analysis. And in case of the energy industries, they employ the Python for renewable energy optimization and predict maintenance, while robotics industries use the Python to develop intelligent control systems and automation solutions. So we will just look into the applications one by one in various industry. So we could see how the Python has evolved into a universal engineering tool, which has been used across all the major industries. First, let us talk about the mechanical engineering application. See, we've already talked about various application. So we have got the vibration. So for example, you have the vibration analysis. This will help the engineers to understand the oscillation in rotating machinery. So how the excessive vibration can cause fatigue failure and reduced equipment life. That's one application in the vibration. Similarly, when you talk about the heat transfer calculations, so you could see the heat transfer simulation are used in the design of engines, cooling systems, and thermal management components. So basically into the electric vehicle, EV, you have talk about thermal management. You have, I think, few days back also you have heard in the news that EV bus has got fire or something. So that is basically we need to look into the how we could stop that. Basically look into the thermal management of the components. And this is the common one, this restraint plot, which you'll be able to understand easily how you could take the stress strain graph from the tensile equipment and then try to get a plot out of it and then try to understand how you simulate and then understand the behavior of the material, how it fails. So this is the reason why the mechanical engineers start using the Python to predict the system behavior before the manufacturing begins. So the main idea is you predict the behavior, understand failure, and you go with the design with great confidence. Then I got the automotive engineering application in vehicle dynamics, battery modeling, engine data analysis, CAN bus data processing. See, the modern vehicles, as I've already said, it generates a large amount of data through the sensors. So you got the electronic control unit, the ECU, communication system, and intelligent technology. See, managing and analyzing this information would be difficult without the computational tools. So Python plays a major role in processing and analyzing the automotive data. So it is widely used for the vehicle dynamic simulation, which involves braking, steering, suspension system, and ride comfort analysis. So engineers use it to model electric vehicle batteries and predict the charging behavior also. Because this is one of the main thing which we are just trying to look into that. So charging behavior, thermal performance, and energy efficiency. Such simulation will help us to improve the battery reliability, and overall vehicle performance. So when you talk about the other applications like the engine data analysis, so this helps the engineers to improve the fuel economy and optimize the performance. So Python processes the CAN bus communication data, which enables us to have the real-time monitoring of sensors and vehicle system. So this capability is particularly important in modern connected and autonomous vehicle. So now we are into the disruptive technology of electric and autonomous vehicle. So when you try to consider the electric vehicle, the battery temperature directly influences the charging performance, efficiency, and battery life. So the Python, when you're using it, this will allow the engineer to predict the battery temperature under different operating conditions, and you could develop strategies to improve the performance and safety. So in case of the automotive engineering application, so the Python will support the development of safer, smarter, and more efficient vehicle while accelerating the transition towards intelligent and electric mobility. So next, going into the aerospace application. So considering the aerospace application, so basically you need to launch a vehicle or anything that would be very expensive. So why the aerospace engineers heavily depend on the simulation and computational analysis, thereby they could reduce the cost as well as the risk involved in the product development. So in aerospace engineering, the physical testing is often expensive and time consuming, as I've already said. This Python supports the CFD pre-processing, aerodynamic analysis, flight trajectory simulation or prediction, and orbital mechanics calculation. So engineers use it to study the airflow over the aircraft surface, predict the rocket trajectories, and analyze the satellite motion. Through simulation, the aerospace engineers can evaluate multiple design alternatives before they go in for the actual testing. So this will significantly reduce the development cost, improve the safety, and accelerate the innovation. So when you talk about Python helps the aerospace engineers reduce the risk, lower development cost, and improve the reliability of high-value aerospace system. So because you talk about the reliability is should be very high in case of the aerospace because it involves the life, or we could not risk the life of the passengers. Next, talking about the civil engineering application. The engineers use the Python for structural analysis, bridge design, earthquake data analysis, and traffic simulation. So this application will help us to predict the stresses, evaluate the structural safety, and understand the dynamic response during seismic activity, which is the earthquake. So through the computational analysis, engineers can investigate how buildings, bridges, and other structures respond to different loading conditions. The traffic simulation models will help us to optimize the transportation network and reduce congestion. Such analysis support better urban planning and improve the efficiency of transportation. So earthquake simulation are particularly important regions which are very prone to seismic activity, where engineers must ensure structures can withstand the dynamic loading condition. So basically, the engineers can simulate the earthquake loads on building and they can evaluate the structural performance before any construction has been done. So talking about the Python, this contributes directly to the safer infrastructure, improved transportation system, and more reliable civil engineering design. Then next, moving to the next application, electrical engineering application. So basically, we need to build and test every electrical circuit physically before the design validation. So this will be very expensive and time consuming. And also the Python helps in simulation and making it less expensive. So Python is used for analyzing the electrical and electronic systems. Applications include signal processing, communication system, circuit simulation. So engineers use the Python to filter the signals, study frequency response, analyze the system, and then test the circuit performance before the hardware implementation. So Python is also widely used in automation, robotics, and industrial control application. So it has got a extensive library which provide efficient tools for solving the complex electrical engineering problem. So even the communication engineers simulate an entire communication system and they evaluate the performance under different conditions before developing the physical hardware. So this helps the engineers to reduce the development time, improve the reliability, and identify design issues early in the design process. So next, talking about, see this is the main thing which we'll be focusing on. So far we have been talking about why we are going for programming, why we wanted to use the simulation, and why we wanted to have Python. Now we'll be moving into the main agenda or the main picture. So before that, if anybody has any queries or anything, feel free to ask. Actually, we will not be teaching any Python or giving you a code or anything, but we will try to make you understand how Python could be used for the engineering simulation. That is the main idea with which we are just focusing on this. I think I'll move on to the next one. See, this is the whatever the content which we are going to talk. This is the we could say this is the main picture which we are going to talk about. So we are just trying to see what are the steps in modeling and simulation. I think we have already seen how the engineers study the complex system like automobile or a aircraft or a bridge or a robo or battery or any manufacturing process. So everything is being done through the modeling and simulation. So talking about, see, this is the one. So first we have the modeling. So I'll just list down the thing. So first you need to understand what is the system. So the process is you have the system, abstraction, model, so analysis, simulation, prediction, validation, then you have got the measurement. So this is the steps in modeling and simulation. I've just taken it and then slightly improved on it and then try to see how easily I can just give it to you. So we'll not be focusing on the validation part and the measurement part. We'll not be focusing. We'll be focusing only on the what is the system and how we are trying to understand the system and then try to go about that. So when you talk about the modeling, it's a process of simplifying a real world system or the problem that we want to study. So we are just trying to see how we could convert that into the model. So we are just trying to analyze it mathematically or in a computational way. So we are just trying to see the conversion. So whatever we wanted to do, the real world object or the real world system, we are trying to convert that into a model. So we'll just try to see how it's been done. So the model will be able to predict the performance, explain the physical phenomena, support the engineering design, and then you try to see how that model are compared with the real world measurement to verify whether the model accuracy is represents the reality. So talking about the workflow, so the process begins with the system, which I say it's a problem definition. So I say it's a problem definition. So the real world object or the problem that we wanted to study. So this is where the engineers identify the real world object, the product or the problem that we want to study is called the system. So, but most of the times the real systems are very complex. So we'll not be able to understand it in a better way. So that is what the next step is, the abstraction. So you go in for the next step is the abstraction. So what we try to do, we try to simplify the real system by removing the unnecessary details and keeping only the important features. So you try to remove the unnecessary details, whereas you retain the essential physics that govern the system behavior. So based on this understanding, the engineers develop a model. So when I say model, which may consist of the mathematical equation, diagrams, logical relationship, or computer programs, which represent the actual system or the real world system. So once when the model is developed, the next step is the analysis and the simulation, which is performed to study how the system behaves under different operating conditions using mathematical model or computational tools. So the simulation results are then used for the prediction, where engineers estimate the system performance, identify the trend, and understand the future behavior. So however, predictions alone will not be sufficient. So thereby the engineers has to collect measurements from experiments or from the real world system to obtain actual performance data. So the reason why you are performing the validation by comparing the model prediction with the measured value. So you just try to validate whatever you have predicted and whatever you have got the measured value. So only if you do this, if the predictions closely match the reality, the model is valid and can be confidently used for the design, optimization, and decision making. So if significant differences exist, the model must be refined and the process will be repeated. So the same thing, I'll just explain an example of an electric vehicle battery. You're just considering as a example. So engineers begin with the battery system they wanted to study. So they just take the whatever made with the battery, whether it's a lithium ion or the lithium ion phosphate battery. So they simplify the problem by focusing on the important factors such as voltage, current, and temperature, whereas they try to ignore other unnecessary details. Their focus will be only on the major or the important factor which plays a major role in the battery system. For that, you try to develop a mathematical or computational battery model will be developed. Then you have to perform some simulations to predict the charging, discharging, and the thermal behavior. So for that, you take the experimental measurements you can collect from the actual battery, and the simulation results can be compared with this measurement. So if both the results are agreeable, then you can say the model can be used to improve the battery performance, efficiency, and lifespan. So this is how the modeling and simulation process follows a systematic workflow. So basically, you have got a system, which means the what I say it's a problem definition. Abstraction is understanding the physics. Model, you do the analysis and simulation. Prediction, measurement, validation, which will enable the engineers to study, predict, and improve the system performance with confidence. So I'm just trying to repeat it. It's you got the system, which is the problem definition. Abstraction, you got the understanding the physics. Modeling, simulation, data analysis is a prediction, and you got the optimization also. wherein you try to improve the system behavior. So this is the basic structure. Now we will go into one by one. So the first one is what I've said is the modeling. So this is the first step before solving any engineering problem. So before engineers can predict behavior or perform simulation, they must first understand the system and represent it mathematically. So this process is called the modeling, which forms the foundation for the engineering simulation. So we can say modeling involves creating a mathematical representation of a real physical system. The objective is to capture the essential behavior of a system using equations and mathematical relationship. So example we have shown spring mass damper system, which is used in vibration study. Then you got the heat transfer model, which is used in thermal analysis. Beam bending equation, which is used in structural engineering. And you got the fluid flow models, which is used in the fluid mechanics. So basically, when you have a good model, that will lead to a meaningful simulation, and modeling will be the foundation for all the engineering analysis. So the applications of the Python, mathematical modeling, differential equations, and system behavior prediction. The next, we have the simulation. So once the mathematical model has been developed, the next step is simulation. So you can say simulation involves using mathematical models to evaluate the system behavior under various operating conditions. So engineers can study how a system performs, identify the potential failure, and evaluate multiple design alternatives before any process begins. So you can say it's a virtual testing of engineering systems using computer model. So the application comes under the stress analysis and thermal simulation, safety analysis, motion simulation, electric circuit simulation. So simulation helps us to reduce the cost, time, and risk by allowing the engineers to evaluate the designs virtually before the physical implementation. The next step is the visualization. Why do you go in for the visualization? Basically, you could get a clear picture, or when you have the results, you plot it as a graph, and then you'll be able to visualize it in a better way. So engineering simulations, you got a large number of data. When you convert this data or the numerical data into the graphical representation, like line graph, bar graph, or the bar chart, histogram, heat maps, contour plots, and 3D plots, you'll be able to get a clear picture. So visualization helps in identifying the trend, detect the anomalies, compare the design alternative, and communicate results effectively instead of examining thousands of prototypes. Or engineers can quickly understand the system behavior through visual representation. So you could get a what called for example, when you take a heat transfer simulation, a temperature contour plot can help us to identify the hotspot and temperature distribution pattern. Similarly, when you are going for the vibration analysis, the displacements of the time graph can show the oscillatory behavior. So we have got Python libraries such as matplotlib and plotly, which will make the visualization simple. So the next topic after this, we'll be talking about the visualization. What are the tools which are using in the Python? I'll be just running through it. So this makes the visualization simple, flexible, and powerful. So engineers can generate professional quality plots that supports analysis and decision making. So visualization not only improves the understanding, but also enables the effective communication of engineering, which results to the managers, customers, and stakeholders. So We're just trying to represent that's the power or the visualization. So you're just trying to convert the data into meaningful engineering insights and support the better decision making. The next is the optimization. See, I think morning also they have been talking about for a problem, you have multiple solutions. You don't have a single solution to the engineering problem. So you have similarly in engineering, when you have the design, you have multiple design option, but everything will not be at the same level. So we need to see which parameters or the factors we need to optimize. So optimization focus on the finding the best possible engineering solution among the best or the many alternative. So nowadays when we talk about the electric vehicle, we try to see the minimize the weight and then improve the efficiency and reduce the manufacturing cost. So which is the main factor in EV production. So instead of manually doing it, we just go in for this optimization. So this optimization is widely used in structural design, material selection, manufacturing process improvement, and energy system development. So by systematically evaluating the design variables and constraints, engineers can achieve better performance while using fewer resources. See, Python here provides a powerful optimization tool to solve complex engineering problem efficiently and systematically. So by optimization, you are able to achieve the best possible performance while minimizing the cost, weight, energy consumption, and resource usage. The next we have the data analysis. So what is the value of data if you are not trying to analyze it? So we have already talked about that we have large amount of data and we need to see how we need to utilize it properly. So engineering data comes from various sources like sensors, IoT devices to conduct the experiment, testing facilities, manufacturing systems and simulation. So data analysis helps the engineer to transform the raw information into meaningful insight that supports the engineering decision. Similarly, the Python supports data cleaning, statistical analysis, predictive modeling, and then visualization and dashboard creation. So this capabilities help the engineers to identify the trends, predict failures, improve performance, and optimize the operations. So for example, when you have the predictive maintenance system, you need to analyze the equipment sensor data to identify the early signs of failure. So we need to understand how or where the failures occur. For that, you need to do the analysis in advance. So the data is a valuable one which has to be analyzed and transformed so that you get a useful information. That's what the data analysis. So we've got the steps involved in modeling and simulation. So we've got the system, abstraction, model, analysis and simulation. Then you got the prediction, validation, and measurement. So this is what we have been talking about. So next we'll just try to see what is the machines could learn from experience in the same way the machines can do. So that is what you have the AI and ML, artificial intelligence and machine learning. So how that transforms the modern engineering. So the AI allows the system to identify the pattern, make prediction, and support intelligent decision making. The machine learning enables the systems to learn from data and improve performance over time without requiring any program for a particular situation. So we could see the application, the predictive maintenance system analyze the machine data to predict failure, and you got the autonomous vehicle. You got use of the AI to process the sensor data and make the driving decision. Then you got the smart manufacturing. They use the AI algorithm to optimize the production process and improve the efficiency. And similarly, you have various applications like computer vision, robotics, and then you've got a wide range of libraries which helps us to develop the predictive maintenance system or the autonomous vehicles or the robotics application or the computer vision system. So the basic thing is Python is one of the primary tool or the technology which drives the intelligent engineering system through the artificial intelligence and manufacturing. So what is the future of engineering with Python? See what skills you require 10 years from now. So the future of engineering has become increasingly digital, intelligent, connected, and data-driven. So as technology continues to evolve, engineers will require skills that extend beyond the traditional fundamental. So you have the emerging areas like digital twins, smart factories, autonomous system, industrial AI, robotics, and sustainable engineering. So which heavily depends on Python and computational tool. Nowadays, most of the engineers use the virtual models to monitor the performance, optimize the operations, improve the efficiency, and reduce the environmental impact. So the future engineers will need strong foundation in engineering principles, and at the same time, they need to develop expertise in programming, simulation, data analytics, and artificial intelligence. So those who can combine the skills, they'll be better prepared to lead the technological innovation and solve complex engineering challenges. So industries are increasingly seeking professionals who can work with digital technologies, interpret data, develop intelligent system, and support sustainable engineering solutions. So the engineering profession is evolving rapidly, and Python has become one of the key technology, or we can say it's a technology enabler which is doing this transformation. So the future engineer must combine the engineering knowledge with programming, simulation, data analytics, and AI skills. To summarize, so we have seen that programming is essential for the modern engineers, and it is not pertaining only to the computer science department. It is to all the departments, and we have seen it's Python is used because of its simplicity and flexibility, and it's a open source which accelerates the innovation. And also it has been used across various departments: mechanical, civil, electrical, automotive, aerospace, manufacturing, healthcare, energy, and robotics industry. So Python enables, it's been widely used in the industry for the model system, simulate behavior, visualize the result, optimize the design, analyze the data, and develop intelligent solutions. So engineering is rapidly moving towards a digital future wherein we require simulation, automation. So AI and data analytics plays a major role. So the engineer in the future, they need to understand the digital model, and they need to see how they could perform the simulation and analyze the data, optimize the performance, and develop smart system. So as future engineers, they need to combine the engineering fundamentals with programming, simulation, and AI, which will determine how effectively the engineering challenges can be solved. So this is the essential skill for the future engineers. I think with this, I just complete this one. Then I'll just have a quick. So any questions or any queries on this? Any questions or any queries?
Dear participants, if you have any queries or if you have any doubts to be get clarified with the resource person, you can post the question in the chat box. Otherwise, you can directly ask the resource person. Question.
I think one Prakash has
Yes,
asked
sir.
a question. Contact mechanics. See, it is not only used in the what you call the mechanical. It's used in all aspects. So I have just taken some examples so that it will be easy for them to understand. That is the idea with which I have taken it. I have not gone in depth. I have just shown you some of the applications. See, now what I am going to talk about the next application also. It's a simple one so that everyone can understand that, because it's related to the heat transfer. That's also connected with the basic physics only. I think what I've talked is the basic. So what is the Python and how it's been used, and which are the departments or the engineering fields being used, the industries which use the Python. It's not one industry, even in the health also it's been used. So that's what I'm just trying to, I'm not teaching Python or anything. I'm just trying to see how you could make use of it. I'll just show a small program also, the Python program also. Okay, next I will just share the slide. See, I've been talking about the data visualization. Can you see the slide? It shows the screening is paused. I don't know. I'll just. Can you see the slide?
But the
Old
now,
slide.
okay.
Huh?
The last one summary that we were explaining.
But I have closed it, but I don't know whether I need to stop share and then I will try to do.
Yes, sir.
I think now you are able to see the next.
Yes, sir. Yes, sir. It's visible, sir.
See, here I will not touch upon much. This is only a just tell you how the data visualization for the engineering analysis is done with the Python. So I've already, I'm not, I've taken the how to, you already know what is the line plot or anything. I have just taken an example, and then it mostly it will be with mechanical application. So I'll just rush through. I'll just try to finish it within 10 minutes and then go to the case study. So this will help you to understand Python. So how the Python will be able, you can visualize it, how you could make the graph. So the next topic is the data visualization for the engineering analysis using Python. So we have been talking about the large amount of data from experiment, the simulation, sensors, everything. So with the data, we can't do anything. We need to understand and we need to interpret. So if you have the data in a spreadsheet, it will be a little bit difficult for you to present it as a graph. Whereas in this visualization, this acts as a bridge between the data and the engineering decision making. So it helps us to understand the system behavior, compare the alternative, detect the fault, and communicate the results. So here I will just talk about how to create the engineering graphs, different types of plots that has been used in engineering analysis, how to visualize the 2D and 3D engineering data, how to produce the thing, and how you could apply that. So basically, it's not the engineers do not generate the data. We need to see how you could interpret and communicate it effectively through visualization. So that is what the main agenda. So why this visualization is important? Because it helps the engineers to detect the trend, compare the systems, identify failure, analyze the performance, and present the findings. So the engineers deal with large data sets every day. So we need to see. I've just given some examples from various engineering application. The mechanical, you have got the stress strain curves, the vibration. Civil engineering, you have got the load distribution, structural response. Electrical engineering, you have got the voltage time signal, sensor outputs. Automotive, you have got the engine performance map, temperature distribution. Aerospace, you have got the pressure contours and flow visualization. Basically, all the engineering decision are based on the visual interpretation of the data. So only if you have a well-designed graph which can communicate the complex engineering behavior, you'll be able to get the decision very easily. So now I will not go into depth anything. I'll just we'll be talking about the matplotlib. So it's a Python library which is used for plotting and visualization. This is used for scientific and engineering graphs. This produces publication quality figures. This is very easy to learn. MATLAB like plotting. It works with NumPy and Pandas. So matplotlib is the foundation of engineering visualization. So basically, you are just trying to see how you could present your engineering data, you analyze and give a report in a professional way. That's what we are just trying to look into that. So first, the line plot. See, I've already written the code and then taken it to the Jupyter and then executed it. So I'll just show you. You could just see line plot. It's basically a variation of one variable with the other. So in this example, we have talked about displacement versus time. So you could have line plots are primarily used for continuous data. These are widely used in engineering because many data in engineering vary with respect to time and position. So whenever you want to observe some trends, line plots are the first choice we use. So I will just give you what is the significance and then how it's been. I'm not talking about the programming part. So next we have the scatter plot. So this shows the relationship between the two variables. So in this, we have taken an example of engine speed versus fuel consumption. So talking about the engineering application, you've got the correlation analysis, experimental data analysis, machine learning data sets, sensor calibration, and so on. See, the main significance of scatter plot will reveal the relationship that will not be very obvious from the raw data. So this will help us to discover the patterns and correlation between variables. That's the advantage of the scatter plot. So next you have the bar chart, are basically used for comparing categories. So in this case, we are just trying to compare the strength of different materials. So in this case, we have taken 3 different materials: steel, aluminum, and titanium. So we're just trying to compare it. That's why you're using the bar chart. So the application, material comparison, cost comparison, production comparison, and efficiency comparison. You can compare the material properties. So when you talk about the bar chart, so this what do you call it? Simplify the decision making by making comparisons very obviously. You can see the what we could do. So when you're using the bar chart, whenever the objective is comparison rather than trend analysis, you go in for the bar chart. The next is the histogram. They are the powerful tools for understanding the data distribution. So this shows the frequency distribution. Example is the bolt diameter distribution we have taken. I think histogram application include the quality control, manufacturing tolerances, statistical analysis, and especially the Six Sigma studies. So the basic concepts, what you try to understand from this is the mean, variance, normal distribution. This you might have already done in your probability and statistics. So in this, the examples, we have given the bolt diameter distribution. So you could next one is the contour plot. So the contour plot represents the 3D in a 2D form. So each contour line will connect the points having the same value. So the applications include the temperature, field, pressure distribution, stress analysis, CFD simulations. So engineers use these plots because they provide a compact representation of the large data set. So you're just trying to simplify the interpretation of the complex interpretation or the simulation result. So the visualization is very easy. The next is the surface plot. This provides a realistic three-dimensional view of engineering data. So applications include CFD analysis, terrain modeling, and you got the structural analysis and heat transfer. So in this case, you compared with the contour and surface plot, this gives a more understanding of peaks, valleys, and gradients. So this provide deeper insights into the complex engineering system. So your surface plot is the transformation of the mathematical data into visual engineering model. The next is the 3D visualization. So modern engineering problems often involve multiple variables simultaneously. So in such case, this allows the engineers to study the relationship among the 2 or 3 parameters. So example, you have got the structural analysis, aerodynamic behavior, fluid flow, and so on. And in this, we have got a different plots like surface plot, wireframe plot, and 3D scatter plots. So this improves the understanding of the complex engineering phenomena. So when 2D is not enough, then we go in for this 3D model so that you get a clear picture of the system behavior. The next is the real-time plotting. So here you got the graphs continuously update the data as new data arrives. So it keeps on, the application is IoT sensor monitoring, CNC monitoring, temperature control, and smart manufacturing. So in Industry 4.0 environment, this real-time visualization allows the engineers to monitor the equipment continuously and react immediately to the abnormalities. So this helps us to what you call the predictive maintenance and smart decision making. So you convert the live data into actionable engineering insights. The next is the plot customization. This basically you could change the color, you could change the label, you could change the legends, you could markers or the whatever it may be. You could mark it. See here we have just given some blue color and the marker, grid style, everything we have just change it. That's one option. You could customize the plot according to your needs. So basically why we wanted to customize is you get a good readability, presentation quality, and publication standards. So basically you need to have a graph with good details so that you can interpret in a better way. So then is the dual axis plot or the multiple axis. Sometimes we need to compare 2 different parameters on the same graph. So for example, the temperature and humidity we have shown here, and temperature and pressure. So speed and fuel consumption, something like an voltage and the current. So this helps the engineers to identify the relationship and trends more effectively. So the significance of this is you can compare different variables. So this gives a good understanding of the system behavior. See, I've just given you only an overview. So what are the different plots or the ways by which we could represent the graphs or in a better way. That's what we have just shown. I've just taken the using the Python, recorded it when I did in the Jupyter. So otherwise, no, if I show the demo, it will take more time. That is the reason why I've just thought it could be better to have it. And finally, coming to the closing one, we will just go with the case study. It will take another 10 minutes or so. Is this visible, or I need to go out and then come back?
It's visible, sir.
Okay. Okay. See, I think hope you remember what we have been talking about in the steps involved in modeling and simulation. So what I have just I have not gone into one of the simulation because of the time constraint. See now, because this will take another 5-10 minutes. So I thought I could skip that because you already have seen how we could use the Python and then get into the line plot and other things. So talking about the, I have taken a coffee cooling problem. See, what is the problem is, you imagine you buy a hot coffee before you are going to the college. So the coffee temperature is, I've just given the parameters here. The coffee temperature is 90 degrees centigrade. And also you have the cold milk with you at 5 degrees centigrade. The surrounding temperature or the ambient temperature is about 22 degrees centigrade. And you need to travel to the college from your home. It takes 30 minutes. Now you think like an engineer. See, we need to know when we need to add the milk. What is the question is, how can we keep the coffee hottest when reaching the work? So the coffee should be hot so that I can drink in the college. So for that, what you are trying to do, so you can make a guess or anything, you can do some trial and error, but as an engineer, you need to think what are the possible choices. Either you need to add the milk immediately, or you can add the milk halfway or at the destination. Because you have a coffee, which is the temperature is 90 degree. So what is that you require for this? I think let us make it interactive, because already we have talked about. I think it would be better if you could, someone could answer. That would be fine, because I'm not talking about pure engineering. It's basically the physics which we'll be talking about. So I think this is to demonstrate what I have been talking about. So why we are going to use the simulation? Because you'll be getting a faster and you can predict the behavior very easily before testing, because we need to get the data for every 1 minute, which is not possible doing it manually for getting all the data. So in this case, we are just trying to see how we could use the Python to predict how coffee temperature changes with respect to the time. What is the principle involved in it? Anyone? Next step is the understanding the physics or abstraction. This is the system. So the real world system is the coffee cooling problem. This is the problem we wanted to study. That's what I have defined it. What is that will happen? So the coffee, when you add a milk, it gets cooled. What is the principle there? What is the physics involved in it? Anyone can answer? See, it's I'm talking about the daily happening. You are having your coffee daily, coffee or tea, either in the morning or in the evening. So that is the reason why I've chosen this particular problem, so that I'll be able to tell you the engineering concepts also from this. Anyone? So what is the physics behind this problem? Okay, let me put in the other way. Why does the hot coffee become cold after some time? So someone can answer this. Anybody has put in the chat box?
Due to heat transfer.
It's
Hello,
because
I
of
am
natural
audible?
convections.
Yeah, right. Okay. See, because this is the final part, I thought we'll have some sort of interaction. See, I'll just put it. Okay. See, basically, the physics behind this is you need to have the answer is the heat transfer. You need to understand the heat transfer. So you already aware of the heat transfer principle. So when a heat always moves from the higher body to the lower body. So the coffee temperature is 90 degree and the milk is 5. Now the surrounding is 22 degree. So it has to come down. So the coffee is hotter than the surrounding. So heat will continuously leave the coffee and enters into the atmosphere. We already know there are 3 modes of heat transfer: conduction, convection, and radiation. So in the coffee, the primary cooling occurs through the conduction and convection. Because you have the, what you call for this, we need to develop a mathematical model that will represent the cooling behavior. So we need to understand how the temperature changes over time. So first we have gone into the system, you understand the physics. Basically here it's a heat transfer, the temperature, how the temperature changes with respect to the time. For this, we need to go in for the modeling. So we need to develop the mathematical equation. You are all familiar with the Newton's law of cooling. So this equation states that the rate of temperature change depends on the difference between object's temperature and the surrounding temperature. This is what I have given by dt by dt equal to minus r into T minus T environment. T indicates the coffee temperature, T environment indicates the ambient temperature, R indicates the cooling constant. So what is that you are trying to understand from this? See, when you have a larger temperature difference, the cooling is faster. When you have the smaller temperature difference, it takes a slow cooling. See, for example, you have the coffee, you have got the 90 degrees centigrade and surrounding is 22 degrees centigrade. The temperature difference is large. So the cooling will happen rapidly. So after some time, if the coffee temperature decreases to 40 degree, then the temperature difference will be small. Thereby, the cooling rate will decrease. So this we have observed in our daily life. So for this, we need to have the mathematical model which captures this behavior to predict the temperature changes over the time. So this is what we are doing in the modeling, which converts the real world physical behavior into mathematical equation or the mathematical model, which we can analyze and solve it. So talking about the simulation, you need to solve the governing equation. See, I will show the program also. I'll just explain it first. To solve the governing equation, you got the Python simulation process. You start with the coffee temperature, compute the temperature difference, calculate the heat loss, update the temperature. You repeat for every minute. So this is a repetitive and time consuming. So it will keep on doing it. So the simulation starts with the 90 degrees centigrade. It applies the Newton's law of cooling. So it calculates at every point. We are just trying to continuously predict the behavior of the system over time. So this has been done with the help of the Python. So simulation will help us to solve this mathematical model and predict the system behavior. So I've just given some rough data. So next is the visualization. After simulation, we get a lot of numerical data, which we try to take it and then plot it as a graph so that you get the trend, which will be easy to understand. Then you get the expected graph. The temperature will continuously decrease with respect to time. So when you have this plot, you'll be able to identify the cooling pattern and the trends in it. So next is the data analysis. You try to interpret the data. So how the cooling behavior occurs. So how much temperature is lost, how fast does the cooling occur, is the cooling constant throughout the process. So some of the observations you find that initial cooling is faster, as I've already talked about. So initially you have something like a 90 to what do you call it? It's 22, 90 to 22. There is a vast difference. So the cooling rate will be high at the initial stage, and then the cooling rate decreases later on. So it will be something like coming down. If it is 40, it will be having something like a 0.5 degrees per minute. So there will be a cooling rate will be varying. Similarly, the coffee temperature also will be approaching the ambient temperature. So what is the interpretation we are just trying to get from this is as the temperature difference decreases, heat transfer becomes slower. So some of the data we have just taken it. So how the variation will occur. So I'll just run the program also. So talking about the optimization, you try to see how you could improve the system performance. How can we keep the coffee hotter for the longer time? So possible design modification will be you improve the cup insulation. You can use a thermal flask. You can increase the cup wall thickness, reduce the heat loss area, change the timing of milk addition. And also you can go in for the optimization process, modify one parameter, run simulation again, compare the result, select the best option. So you need to maximize the final coffee temperature after 30 minutes. So you improve the design performance without building multiple physical prototype. See, we have seen that cooling is faster at the beginning, cooling becomes slower over the time, and then temperature approaches the ambient gradually. And when you look into the optimization study, when you're having the what you call the high cooling constant, so that will have a poor insulation, high heat loss, and coffee lose rapidly. That's some of the worst design. When you go in for something like 0.01, so this will be something like a moderate insulation and moderate heat loss. So when you have something like a cooling constant is 0.005, so that will give an excellent insulation, low heat loss, and coffee will retain heat much longer. That will be the best design. So this means the in the optimization, you need to see how you could have the cooling constant at the low value so that you could get a better results. So this is some of the results which will be getting it by the optimization. I'll just see this is I will show the program also. See, we're just getting the simulation as well as the visualization. So you got the simulation result. So the initial cooling rate is 0.6 and final cooling rate is 0.50. So similarly, the cooling constant, what I've been talking about, 0.02, 0.1. So how we are getting the lower cooling constant, you're getting a better insulation. Higher final temperature, the heaty, you get a better design. So this you could achieve by using the Python. I'll just show you the content. See, okay, I'll just finish this one. So talking about this, to summarize, we can say the problem definition. You define the engineering problem, understand the physics. In this case, it's the heat transfer principle. Modeling, you develop the mathematical equation, you use the Newton's law of cooling. Simulation, you solve the equation using the Python. Visualization, you plot the temperature variation. Data analysis, you interpret the cooling behavior. Optimization, you improve the system performance. See, this finds the real-world application, vehicle cooling system, battery thermal management, and aerospace thermal protection and industrial heat treatment. These are the applications. I will just show the program. Yeah. Can you see the screen? Yeah.
Yes, sir. Yes, sir.
Yeah. See, this is what we have just, what I've been, how we are just using the Python. So you use the plotting one, then you try to see the problem definition, whatever the problem we have defined it. Then we have gone into the simulation. Then you applied the Newton's law, and then you're trying to visualize. That's why you're getting the graph. And then we are trying to see, they analyze the data, and then you try to get what is the cooling rate, and then you try to do the optimization study, the cooling constant, and then try to arrive at that. That's what the thing I was showing to you. So with this I just come to the conclusion. So we have been talking about the Python for engineering simulation. We have understood what is the different ways by which you can apply the Python for various engineering domain, and the steps in modeling and simulation. You got the system, which is the problem definition, abstraction, understanding the physics. Then I got the modeling, simulation, visualization, data analysis, and optimization, with which you can go in for the better design. So I've just taken an example of an heat transfer, which is a basic physics, which you can understand. This could be applied to the electric vehicle or anything, and then you can solve the problem. This could be applied to any domain also. It is not pertaining only to the mechanical. It could be applied to any domain. See, is that clear? So I think I just conclude. It's 4 o'clock. I just finish it.
Yes, sir, it's clear.
Is that okay?
Yes, sir. Yes.
See, I think is Jupyter a different package, or is it? See, it's a Python only. We are just trying to run in the Jupyter. It's a same thing only. It's not different one. It's a Python. I'm just running the Python program. When you just download it, you can get that. You'll be able to do it. If possible, can you show a simple program? Okay, I think I've shown the simple program to model or simulate a simple system. How to integrate the programming with, no need to explain. I think I've shown that. Paul Durai, SVCE. Paul Durai, you asked a question. Is that okay? Paul Durai from SVCE has asked the question. I think I have answered that. And contact mechanics, large deformation is possible in Python. Yes. Say all sort of problems you could solve the complex problem in using Python. Prakash, AP Mechanical KIOT. And Dhanapal SVC, is it structured programming language like Fortran? Yes, it's a open source. It could be used something like a C. Now this is getting a popular one. It's also like the C, C++ only. But only thing is it's open source. I think any other questions? I think that's the questions there in the
Yes.
chat.
So thank you, sir. Thank you very much. Dear participants, if you have any queries, you can ask the resource person. Thank you. Thank you, sir. Thank you very much.
Thank you, Paul.
Yes, sir. I take this opportunity to thank on behalf of Department of Mechanical Engineering, Knowledge Institute of Technology, especially the session that you have explained in detail, the Python for engineering simulation. That was really well presented, sir. Thank you very much. And dear participants, if you have any queries, you can send the questions. Okay, we can get clarified with the resource person later also. So he's
you can get in touch with me later also. Yes. See, I'm not. It's not focused on the writing a Python or anything. It's basically how you could use the Python for engineering simulation. That is the main theme. So my entire thing was focusing on the Python, and then what are the steps involved in it, and then how to do that. That's the idea.
Yes.
It's not writing a program. Either you should be aware of that, or you need to learn, and then you try to do it. At least you know that Python can be used in various fields. How it could be made easy for you.
Thank you, sir. Okay. HOD sir, if you want to make any comment, you can just.
Yeah, sir. Thank you so much, sir. Normally, post-lunch classes will be somewhat bit tough to follow by the faculty members. You made the entire program very interestingly, Professor.
Thank you.
Thank you so much for accepting our invitation and delivering a hardcore topic to the faculty members of mechanical engineering fraternity. I hope your session will be a great eye-opening for all of us, and we'll take up to our college level to implement and to see the changes in the hierarchy thinking level kind of assessments and everything.
Yeah.
Thank you so much, Professor. Thank you so much.
Thank you.
Thank you, sir. Thank you.
Yeah, thank you.
An announcement, dear participants. Okay, the end of first day is over of a 6-day faculty development program, and tomorrow morning, the second day session, okay, will begin at 10 a.m. exactly. So you are expected to join the session at 9:45 so that we can start the session by 10 a.m. sharp. So I request all the participants to join the session 9:45 a.m. tomorrow morning for the first session, so that we can start the session exactly by 10 a.m. Thank you.
Okay. Thank you, sir.
Sir, HOD sir, if you want to make any announcement to the participants, or shall we?
No, it's going quite. No issues at all.
Thanks, sir. Okay.
Thanks, Anand. Thanks for your whole day cooperation.
Thank you, sir. Thank you.
Yeah.
Thank you. Okay. Thank you very much for all the participants for your active listening throughout the session from morning to this time. So thank you very much for your patient listening, and also hope all the 3 sessions, okay, would made you eye-opening to the topic smart machines 4.0 and Python and etc. Thank you. Meet you again tomorrow. Have a good day.